All right. Good morning, everyone. Good morning. Good morning. It is lovely to see a lot of you. I know it's the last day of ICRA. It's 9 a.m. But you know what? You guys are the troopers. I'm super, super excited to see a lot of faces here and get to talking about safety for vision language models in robotics. We're going to do a quick round of intros. We're going to talk about both the organizers and the program. And to kick us off here, I'm going to have Thomas take it away.
Okay, so welcome everyone. So my name is Thomas. I'm a final year PhD student at UC Berkeley, and I work on safety and alignment for robotic systems. And it's super happy to be here today to introduce our workshop and chat with you guys.
All right. Hi, everyone. I'm Rowan. I'm a fifth-year PhD student at Stanford. My research broadly focuses on reliable machine learning for autonomy, particularly when robots face out-of-distribution conditions with respect to their training data. Very excited for all the talks today and all the comments and questions and discussion we're going to have at the poster sessions.
All right. I'm the last organizer here present in person. My name is Andrea Baichi. I'm an assistant professor at Carnegie Mellon University. Super broadly, I'm interested in embodied AI safety. What does it mean? How do we do it? And this is why this is a very timely topic. We have three other co-organizers who could unfortunately not make it here today. We have Andy Peng, Kritarth Goel, and Ed Schmerling as well. So if you ever see them, please say hi.
Awesome. Okay. So I think everyone will agree that the past 1 or 2 years are super amazing, right? The rise of the foundation models is changing like how we design robotic systems. And these powerful models are pushing robots into these increasingly complex environments and novel settings. And now we are seeing that these amazing fully self-driving cars are starting these ride-hailing services in San Francisco and other countries as well. And also we are seeing these assisted robots entering our homes to help us. And for the first time, we as normal human users, we actually feel that these robots are operating closer to us. So however, like while we are enjoying the benefits brought by these models, we must face the fact that these robots are safety critical systems. And a foundation models, a single error in language interpretation or a misalignment or a delay in the inference time could cause safety critical accidents. So it is precisely this integration of these foundation models introduces new safety challenges in robotics. And by tackling these challenges, there might be new exciting opportunities for us to develop foundation models that are not just capable, but also reliable, safe, and trustworthy. So to make this more concrete, let me give you an example. So this is Google's new Gemini robotics model, a super impressive model. So we can see here the user is trying to ask the model to upright the plant. And it's amazing that it's super powerful. And it coordinates both its arms to upright the plant. But if we look more closely, and we can see that the robot is using like the plant itself as a contacting point. So the execution might be successful, but in real life, this is super dangerous. Like we don't want our robots to destroy our plants. So this brings us the key challenge. These foundational models may like to understand about these nuanced specifications. And this is exactly where these new opportunities might emerge, like the opportunities for us to design these safe foundation models for robotics. And the foundation models are not just like shaping assisted robots, and it's also impacting this self-driving industry. So if you have worked on training models for self-driving, and you probably noticed that the construction zoom is super hard for this traditional end-to-end planning. This is example from Tesla, and we can see that the pilot is driving his car to a construction zone. And surprisingly, this type of issue can actually be solved by foundation models' common sense reasoning capabilities. However, in order to use this amazing common sense reasoning ability, we must address the latency issue and the physical grounding and reasoning issues that come with these foundation models. So we believe that now is precisely the right time to bring together experts from both academia and industry to tackle these problems, to confront these challenges and unlock new possibilities for safe and capable robotics foundation models. So the goal of our workshop is to identify the emerging safety topics and opportunities across the entire development cycle of robotics foundation models, from training to fine-tuning to deployment in the real world.
All right. Thanks, Thomas, for the introduction. I'm going to overview very briefly the program that we have scheduled for today. And so because the safety challenges that Thomas was highlighting are so broad, we also see the submissions to this workshop spanning a wide range of topics, right? We have contributions on benchmarks and data sets and the diversity therein, model fault diagnosis, a number of works on fine-tuning and preference alignment after the initial training phase. We have a number of works on runtime safety verification and interventions that preserve safety. And we also have a number of works that broadly focus on integrating foundation models and leveraging them for robotics in ideally a safe way. We're also very happy to boast a fantastic lineup of speakers from both academia and industry that are going to talk about a similarly wide range of topics and applications, ranging from things like autonomous driving to manipulation. We also have some speakers coming to us from outside of robotics in the core ML community to give us a view of how the NLP community is thinking a little bit about safety challenges themselves. In addition, we're going to get a product-focused view from Sagar, who is a tech lead at Taleo. Am I saying that right? Taleo, which is a startup focused on developing autonomy solutions for heavy machinery. We're going to feature 4 student oral presentations that the reviewers of our workshop deemed particularly interesting. We're going to split these into 2 sessions across the major themes of visual and textual robustness of vision language action models, and the second theme of alignment and generalization in robotics. We're going to have 2 sessions of lightning talks to introduce the other papers that you will see at the poster session. The first session is in the morning, and the second session is in the afternoon. Another thing that I think is interesting for us as organizers is to see if the discussion and the presentations during the workshop today have an impact on your opinion on safety and your opinion at the intersection of safety and foundation models in robotics. So we thought we'd take a poll. So please take out your phones and scan the QR code and fill out the poll and see if you think, are foundation models going to be a risk for robotics, or are they going to help make robots safer? And then at the end of the day, we're going to go and take a look and see if you change your mind. I also want to give Thomas a big shout out for taking the lead and bearing the brunt of the organizing work. So this is really all made possible by Thomas. So I'll give him an applause.
Thank you so much.
Improvement for the second workshop on the foundation on safely integrating vision language foundation models. Amazing. Okay, hopefully everyone had a chance to take a screenshot of this. We're gonna welcome our first speaker, Professor Macropone. If you want to come up and connect your computer.
Yes. Sorry about that. Sorry about that. Yeah. So, get it.
That's good, right?
Mute and change
the source. It should be external headphones.
Yeah, perfect.
And the microphone should be same as system? Or?
Yeah, it's good.
Okay. Awesome.
You should allow me.
Oh.
my sharing.
Amazing. All right. Yeah, and then probably desktop too for you, maybe.
It works.
Looks good. Oh,
Yeah.
amazing. I'm gonna do a quick intro for you.
Yeah.
All right, it is my great pleasure to introduce Professor Marco Pavone. Marco is an associate professor at Stanford University. He's also the director of autonomous vehicle research at NVIDIA. His main research interests are in the development of methodologies for the analysis, design, and control of autonomous systems, with an emphasis on systems such as self-driving cars, autonomous aerospace vehicles, and the future of mobility systems. Marco has many awards. Some of these include the Presidential Early Career Award for Scientists in Engineering, the Office of Naval Research Young Investigator Award, the NSF Career Award. The list goes on and on and on. But instead of listing all of his accomplishments, I think I want to give the stage to him so he can tell us a little bit more about ensuring physical AI safety. Marco, take it away.
All right. Thank you so much for the kind introduction. And good morning, everyone. So today I'm going to talk a little bit about our research toward leveraging foundation models to boost the capability of autonomous robotic systems, and also about our research about developing tools and techniques to ensure their safe deployment. The focus of this presentation will be mostly on autonomous vehicles, with understanding that the results apply more broadly to general physical AI systems. Now, the premise of this talk is that the foundation models provide the key opportunities to dramatically accelerate the development of autonomous robotic systems. Here, by a foundation model, I mean a model that has been trained on broad data, typically in a self-supervised manner and at internet scale, that can then be adapted or fine-tuned to different downstream tasks. Example of foundation models include large language models, vision language models, video generation models, and more. Actually, NVIDIA has a catalog on its website of ready-to-be-used foundation models that you can play with. Now, we're not yet at the level of a giant model that can ingest any data modality and it can be adapted to any possible task. But this idea of pre-training on very broad data and adapting the model to specific downstream tasks has been proven extremely useful in a variety of different settings. So the question then is how we can access and leverage the generalist experience for the purposes of robotic system development. And the answer is in multiple ways. Foundation models can empower several aspects of the AV development process or robotics development process, from offline processes such as, for example, auto labeling of the data or simulation, all the way to the onboard stack. In other words, foundation models provide a key opportunity to rethink the entire AV development process. In this talk specifically, I will be focusing on leveraging foundation models as part of the onboard AV stack, and then I will discuss the strategies to ensure the safe deployment. Now, as mentioned at the beginning, foundation models hold the promise to allow us to drive better and to perform better through more generalizable reasoning. But do we have actually had evidence for it? So last year, we explored this question through our work, Agent Driver. I confirmed that actually there is potential. In short, Agent Driver is a large language model embodied agent that loosely replicates how humans drive, by essentially calling on demand different capabilities, such as, for example, planning or trajectory forecasting, detection, tracking, and so on and so forth. And everything is orchestrated through a text-based interface. Of course, that's not how you would architect an autonomous stack that will go on the car. The latency is pretty terrible, but this is more of a science experiment. And the results are essentially captured by the plot on the right-hand side. On the x-axis, you see the percent of AV-specific data that is used to fine-tune the model. And on the y-axis, you have different metrics, different KPIs. The detailed numbers are not too important. So we benchmark the performance of the foundation model pre-trained model against one of the best state-of-the-art academic models out there, UniAD. Essentially, what you can see is that with just 1% of the data, the model already achieves performance that is better than the performance of the best academic state-of-the-art model, which is normalized at which is equal at 0.3. And of course, the more AV-specific data you get, the better the model becomes. And here there is no black magic. So the reason why Agent Driver only needs 1% of the AV-specific data that is needed to train UniAD is because it leverages all the knowledge that has been acquired at the internet pre-training phase. So there is promise. Then the next question is, how do we best leverage foundation models as part of NAV architecture? Of course, how you architect an autonomy stack is a very broad topic, and the design space is huge. And in the paper that we presented last year at the CVPR, we proposed a computational graph of paradigm to model the general driving task and evaluate the different possible architectural choices in terms, for example, of the necessity of a given module, the relative dependencies across modules, or the type of, or the way that an information is represented, for example, in terms of latent features or explicit outputs. And I'm quite excited about this work, as it provides one of the first ways to quantitatively assess many different architectural choices. Thanks to this framework, we were able to characterize many different possible architectures, and the result is interesting and perhaps even surprising. It turns out that one of the simplest possible design, parallelized design, seems to be the one that performs the best. We refer to this architecture as a paradrive, and this architecture essentially entails a transformer that takes in as an input multi-camera images and it produces outputs for 4 tasks in parallel: mapping, motion prediction, occupancy prediction, and motion planning. Importantly, paradrive follows the principle of train heavy and infer light. So at training time, all parallel heads are necessary and crucial, as the co-training of the different heads allow to make sure that the learned features encode the different key driving tasks, like, for example, occupancy prediction or motion planning. But then at inference time, we only infer through the motion planning head, which provides key latency advantages. And we show that with respect to, again, state-of-the-art driving models, this architecture works better and is safer. And interestingly, the additional heads that are used primarily for co-training, like, for example, motion prediction and mapping, can be optionally exercised at inference time, for example, as monitoring signals. More on this later. So encouraged by these preliminary results, we further extended this architectural archetype with 3 core lessons from the design of foundation models. First, the use of scalable self-supervised losses, like, for example, language generation or video generation. Second, a tokens in, tokens out autoregressive architecture, which itself could be a pre-trained architecture, like, for example, a vision language model. And then the use of internet pre-trained foundation models for tokenization. And to evaluate this foundation model empowered design, we implemented a version of the model that uses a video generation as an auxiliary training loss and an autoregressive backbone trained from scratch. And to assess performance, we leverage an in-house neural reconstruction-based simulator. And in this video, we can see that the model executes an unprotected left turn, in general, a challenging driving scenario. But more importantly, we saw that with this model, we can achieve a performance with a fraction of the resources needed to achieve similar performance with, more classical stacks. So encouraged by these results, we took this model to the vehicle. So here you see the model actually driving in traffic for several minutes with no intervention. So this is actually drive from around the NVIDIA headquarters in Santa Clara. Interesting also, these drives confirm that our closed-loop neural simulator provides a KPI information that is very much correlated with the real-world results. More on this later again. So going one step further, we experimented with using an internet pre-trained vision language model as the core autoregressive backbone. And immediately we see improvements in trajectory prediction on two different fronts. So if you look at the plot on the right, so on the x-axis, there are the amount of epochs used to train the model. On the y-axis is, again, one of the metrics we use to judge the quality of the model. And as you can see, the model that leverages pre-trained large language model, language pre-trained backbone, depicted in blue, converges faster and to better steady state, which essentially means that the language pre-training synergizes well with the task of driving, corroborating our earlier results. So this was very encouraging for us because it shows quantitatively that there is actually a clear advantage in using language pre-trained backbones on production grade data. So we also conducted closed loop evaluation of this language pre-trained model. Here you can see the model performing a variety of difficult maneuvers. And now we are in a phase where we are actually prototyping this model, but this basically ends as much as I can talk about this model publicly. Instead, I want to then focus on the next steps, more on the research side. As all of you know, recently there has been a shift from training time intelligence to test time intelligence. So recent models have demonstrated superior performance to humans on a variety of multi-step reasoning tasks. For example, NVIDIA has developed Cosmos Reason 1 and even a 1.5 billion parameter model that is very capable in terms of advanced reasoning tasks. 1.5 billion parameter model is something that actually you can field on embedded device. So this gives us hope that actually we can usefully use these models also as part of AV and robotics development. So why is this important for autonomous vehicles? Well, of course, autonomous driving ultimately is a reasoning task. You have to reason about counterfactuals, like, for example, what will happen if the pedestrian were to cross in front of me, and so on and so forth. And of course, a so-called reasoning model allows you to more directly reason about different potential logic pathways. It also improves interpretability of the model, potentially also explaining in a way what the model is thinking when predicting a given action. And the signals can also be used as a monitoring signal as part of a broader runtime monitoring architecture. But of course, reasoning for embodied applications is different than a free-form reasoning with large language models. Of course, the model has to take into account the physics of the system, the strict limitations in the compute time, and the safety critical implications of the reasoning traces. So to approach the problem, what we do is to post-train the model in structured ways that we ground the chain of thought predictions into the structure of the driving task, like, for example, reasoning about lanes, maps, and so on and so forth. And then we output a different form of reasoning traces from compressed meta actions all the way to long chain of thought reasoning. Of course, if you want to train a model on this more advanced reasoning task, you need to devise an auto-labeling pipeline that allows you to compute all these reasoning traces at scale. And this is challenging because it's not just about tagging bounding boxes or trajectories. We need to generate an interpretable, grounded explanation of what's happening in the driving scenario. So to handle this complexity, we break the pipeline into different steps. In the first stage, we use a rule-based method to generate the initial meta actions, like, for example, this is a lane change, or this is actually a stay in lane, or this is a stop at the stop sign, and so on and so forth. Next, we bring in large vision language models, such as Vila or Eagle from NVIDIA. And these models analyze the visual frames to identify critical objects and understand the scene dynamics. And then we use an advanced reasoning model, like, for example, DeepSeek R1, to then take all of these inputs and then generate a chain of thought traces and policy-ready meta actions that we can use for post-training. So here's an example that walks through the full chain of thought reasoning process. The system first analyzes the surrounding and identifies critical objects. In this case, there are 4 of them. And there is one in particular that is concerning, so a vehicle that is cutting ahead. The model then, the auto-leveling pipeline then enters the reasoning phase and generates a guided chain of thought explanation that you can see here. And once we've generated the chain of thought explanation, then we generate the meta actions that can then be used for post-training. So with this high-quality chain of thought data, then we can fine-tune our vision language action model. And on the left, we show the benefits of doing so. On the x-axis, we have the different models. The baseline is essentially the model that I showed you before. The second bar is the model that is post-trained with meta actions. And then we further improve the model with post-training with. And this is performance on a subset of the data set that is particularly challenging. Of course, you don't see much performance improvements on nominal cases where you just have to drive straight. And then, as you can see, with just post-training on meta actions, you get about 20% improvement and much further improvements if you further post-train on chain of thought reasoning traces. Interestingly, the model seems to actually understand, in a way, meta actions. For example, on the right, we show two instantiations whereby we use the meta actions as a conditioning inputs, and we see that actually the model generates trajectories that respect this conditioning input. Like, for example, on the bottom left, we tell the model to drive straight, and all the trajectories that are generated drive straight. Or for a similar scenario, we have a meta action as a conditioning input that say that you have to turn right, and then the model naturally turn right. So essentially, the model reasons what understand what a meta action is. Now, of course, chain of thought reasoning is not the only way to shift toward more test time intelligence. There are other ways as well. For example, in another parallel work, we have investigated test time intelligence through the lens of action sampling. Specifically, what we've tried here is to fine-tune a vision language model on a synthetically generated dataset to act as an action evaluator or verifier in a sort of plan and then verify type of planning paradigm. Then at inference time, we seed an action proposal distribution and then rank the different actions that are generated through the verifier, and we pick the best one. And interestingly, we see some nice inference time scaling laws similar to the ones that have been observed recently earlier this year for disembodied large language models, where we see that as we increase the number of samples, so that basically the amount of compute that we do online, then the performance nicely decreases, as shown by the red curve that essentially performs this idea of sampling multiple actions and then verifying them. Of course, the more compute you do at test time, the greater the latency is. So there is a sort of a sweet spot between it. Okay, so it seems that actually foundation models provide key opportunities to improve on board stack, but there are a lot of concerns, and this goes back to the theme of this workshop about fielding foundation model empowered designs in safety critical systems, and rightly so. But what I will claim is that while all of these are valid concerns, it's important to recognize is that foundation models are not black magic. They're essentially large data-driven models, and the automotive community, for example, has a long experience in fielding data-driven models in an automotive product that is, of course, safety critical. There is, in general, no silver bullet in order to ensure safety for a safety critical system. I typically like to think about safety assurances in terms of how they impact the product lifecycle, from design time guardrails. So these are steps that we take in the design and training of foundation model-based autonomy stacks, for example, ensuring that the models are trained on safe behaviors. Runtime guardrails, so these are steps that we take at runtime to monitor that the architecture is performing well, for example, to monitor for anomalies at the input, whether the model is operating in or out of distribution, to monitor the model at the output, or to monitor the model through internal signals that are then cross-checked with other signals to arbitrate, for example, between an end-to-end model and a more classical modular model that could act, for example, as a contingency planner. And finally, verification and validation guidelines, making sure that the models obviously are tested thoroughly. Now, of course, safety is not a linear process, even though I depicted these three guardrails in a linear fashion, is instead an iterative process. Accordingly, the notion of a safety data flywheel is key behind the development of physical AI, where you constantly understand what the pitfalls of your model are, and then you retrain the model, and so on and so forth. Now, excitingly, several of our research results on the topic of AI safety have been integrated in a program NVIDIA that is called NVIDIA Halos. As announced at the latest GTC conference by NVIDIA CEO Jensen, Halos is a comprehensive safety system for physical AI safety, and fortunate enough to serve as its tech lead. And in the rest of the talk, I will focus on two key components of Halos. The first one is how we can use a simulation for validating foundation model empowered stacks. And the second one is once we have a technique to really validate the system at scale, how we can improve them until we meet a given safety KPI. So let's start with the topic of simulation. So of course, simulation has made very significant advances in the past few years, and now is used significantly both for testing purposes and even training purposes. But one important thing to recognize is that for testing and training purposes, you are typically more interested in directional information. So whether, for example, a given policy is better than a baseline policy. The specifics of the number are not too important. For validation, instead, you really care about the specific of the number. For example, you want to understand whether the mean time between failure for your model is some number X, and then compare that number with a safety requirement that itself is a function of the product that you are developing. So as I said, simulation is making progress. So a natural question to ask is whether now simulation is so good that actually we can also use it for validation purposes because we really trust the numbers that it spits out in terms of the metrics. So this brings us to the question of how realistic is a simulator should be. So how good is good enough? So this is a very difficult question to answer, and it requires real world data to validate the simulator itself, which in itself is challenging. But also, if you change the policy, it's possible that the policy now might be more sensitive to different aspects of the inputs for which you don't know if the simulator is a good, faithful replica, which means that you have actually to revalidate the simulator with real world data, which defeats the purpose. So a more pragmatic question that we have addressed recently is that of how we can best leverage real world data and simulated data in a way that reduces the amount of real world data in order to achieve a certain level of confidence in our estimate for the safety KPIs. And for this, we turn to techniques from Monte Carlo variance reduction. So of course, there are several axes that encompass validation, but for this work, I frame the problem of validating the system as a problem of estimating a random variable of interest, which I call F, through Monte Carlo estimation. So the simple Monte Carlo estimator is the average, the empirical mean of the sample that you get from the target environment. Now, the variance of this estimate is proportional to the variance of the metric F itself, and then inversely proportional to the number of samples that you use in order to estimate the mean of this random variable. We don't control the variance of F, but the variance of the overall estimator can be reduced by increasing the number of samples. Now, to do better, so to basically decrease the number of samples needed in order to achieve a given level of confidence, with understanding that the variable F is the one that is difficult to sample from, it might represent performance in the real world, we turn to a particular techniques in variance reduction, which is referred to as control variance. So control variance is a correlated signal whose expectation is known that can we measure on each sample in addition to the metric of interest. So let's assume that we have a control variate that we call G. Then we can estimate the true mean of F by taking the empirical mean of the difference between F and G, and then adding back the expectation of G. Of course, if you take the expectation of that expression, you still get the expectation of F, because the expectation empirical mean of G plus the expectation of G cancel out. So what do we do this? Intuitively, if F and G are correlated, the estimation of the difference has a lower variance than estimating a random variable itself. Intuitively, if F and G are correlated, basically when you take the difference, the noise cancels out. And so basically you reduce the variance. So we can show that for an optimal choice of beta that can also be estimated with data, the variance reduction is proportional to 1 minus rho square, where rho is the coefficient of correlation between F and G. So the more F and G are correlated, the less the number of samples needed in order to achieve a certain level of confidence. So with model sync capabilities, then a reasonable question to ask is whether we can use simulation measurements as a control variant by pairing each real-world test with a simulated test of the same policy on a reconstruction scenario. But a key challenge here is that we don't know the expectation of G, so basically the expectation of the metric in the simulation environment. So our solution here is to leverage additional simulation-only measurement to estimate the expectation of G, with understanding that simulation is something that we can run fast. So these simulation-only measurements can be obtained by testing the latest policies on scenarios sampled even under previous policy rollouts with the different policies. So in this setup, we can show that the variance for the overall estimator is very similar to the variance of the previous estimator, but the correlation coefficient is multiplied by k over k plus n, where k is the number of simulation-only samples and n is the number of samples gathered from the real world. As the number of simulation sample k goes to infinity, we recover the same 1 minus rho square reduction we had before. Now, so if you have a simulator that is very much correlated with the real world, then that's nice because you can get away with far fewer real world samples. And I'll give you a little bit better characterization later. But what if your simulation is a bit imperfect and your correlation is a bit low, maybe 0.5, 0.6 or such? Well, there is something else that you can do. And in particular, you can think of introducing a metric correlator function that takes in your surrogate metric, the one that is not very well correlated, and some foundation model features that encode the different aspects of a scenario, and transform that surrogate metric in a new surrogate metric that is better correlated. Here, using foundation model features is very important because in order to train this metric correlator function, you need a small subset of paired real world and simulated data. So you have less real world data for your estimation. But using foundation model features, we can get away with training this with metric correlation function with far fewer data. And this is reflected here, where we show on the x-axis the percent of pair data used to train the metric correlation function, and how the correlation between the new surrogate metric and the real world metric is. And you see that it increases, but with understanding that, of course, you don't want to use all your real world samples to learn this metric correlator function, otherwise you have left with nothing to do your estimation. So we tested this procedure on a number of different settings. And long story short, since we're running a little bit short on time, and I'll go through all your numbers, is that for a number of different settings, like for example, using open loop metrics to estimate expensive closed loop metrics, or using closed loop metrics to estimate real world data, we can see a reduction in the number of samples from 2x even to 10x. So this is for a given level of confidence. So this, I'm kind of excited about this work because it's one of the first ones to try to look at the problem of using simulation for the purposes of validation in a more quantitative way. So quickly, assuming that now we have a good technology to find errors in our policy, how do we correct our policy? So here shows some of the interesting examples about how a policy might fail. This is actually from the robotics domain. For example, an end-to-end policy might lack the precision to tie a cleat, or might choose a fragile pushing strategy when tacking a box underneath the shelves, or might ignore other objects, dropping books when trying to pick up a book, and so on and so forth. So how we can systematically identify these root causes and improve, and thereby improve end-to-end policy performance. Now, for policy trained end-to-end, as it is typical for foundation model and power policies, you don't really have a control logic that you can change or improve in order to improve the behavior. So somehow you have to relate test time behaviors to the quality composition of the training data. But how can you do that in a principled way, particularly taking into account all the different failure modalities that you might have due to poor data, like for example, in terms of mixed skills of human demonstrations, or some strategies, your data lake being more fragile, or maybe some spurious correlations that are picked up by your policy. So to systematically identify all these root causes, our key insight is to develop methods to counterfactually reason about the impact that inclusion or exclusion of training data has on policy performance. Concretely, we want to answer counterfactual questions about the training data, like, for example, how does the expected return change if we were to remove some demo from the training data, a process that we refer to as data attribution. To do so, we perform data attribution using something referred to as influence functions, which is not a new concept. Actually, it's been around in the machine learning community at least for the past 10 years or so. And this process effectively entails computing a first-order sensitivity around reweighting a training sample. Specifically, assume that you add to your typical behavioral cloning objective the upweighting on one training point, one trajectory. Then what you want to compute is the influence of that sample on the policy performance. That is, you want to understand how change in expected return, you want to characterize the change in expected return with respect to the importance weight epsilon. So this is different for a number of reasons. One, because the return is the result of action sequences on a longer horizon. And second, because we don't know the dynamics of the environment, so we don't have a closed formula for the function J. So our insight is to apply policy gradient tricks to basically rewrite this influence function into something that is computable, essentially decompose the performance influence into a tractable sum of the influence of the log action likelihood of the probabilities. And we should actually, this allow us to filter a lot of bad training data, or actually add the data that is deemed as maximally improving. And we see that our method that is called Cupid, which is a very nice acronym that Rohan and my student came up with. I was very annoyed to, well, not annoyed, but a little bit saddened to hear that actually ChatGPT generated this beautiful acronym. But anyway, Cupid, curating data your robot loves, I think is a nice acronym. And this seems to be a promising way to principally relate closed loop performance to specific data, and then thereby helping you in reasoning how to improve the composition of your data. So I will wrap it up very quickly. Of course, foundation models also provide opportunities to improve the safety of a stack, for example, by designing better runtime monitors. And we have tested runtime monitors in a variety of scenarios. That said, thank you for your attention. I think that the potential use of foundation models in robotics is very exciting. Of course, as mentioned by the organizer, there are safety considerations about feeding these foundation models, but we have several tools at our disposal. And I look particularly at the topic of safety through different lenses. The first one, how we can use simulation for validation. The second one is how we can, in a more principled way, relate closed loop performance to specific data points in your data lake to retrain in a more targeted way.
Thank you so much, Marco. That was a really, really great way to start off the workshop. We're going to have our next speaker set up, but we have time for questions. There are microphones over there. You can line up if you want. I can also come to you. We already have, hold on, I saw a hand here first.
Hi, Marco. Thanks so much for the talk. That was awesome. I have a two-part question. So you talked about the verifying safety through simulation. So what is safety for you in this context? And there's an underlying assumption about the distribution of the world, right? So what happens when the real world, and Ithaca, New York is not sunny San Francisco, right? So how do you think about that in that context? Or is making kind of for a specific set of environments, specific the distribution check for people?
Yeah, so both excellent questions. So first of all, quantifying safety is indeed a very difficult question, particularly in autonomous driving domains, where, for example, I mean, of course, you don't want to collide with things, but the notion of safety is much more nuanced. In general, you don't want to create unreasonable risks to other people on the road. Okay, what is reasonable and unreasonable, and what do we mean specifically by risk? So for the experiment that I show, I was using a typical safety metrics, like, for example, time to collision or displacement error with respect to an expert trajectory. But in reality, actually, you use many more safety KPIs. And one important thing is that some of these KPIs might be actually data-driven in order to better capture the nuances of what reasonable or unreasonable risk is. At GTC, actually, we had an AV safety day where we went in great lengths in terms of what it means to actually measure safety, and we can have more of a discussion about it offline. The second question is equally important, is that of input coverage. And that is not something specific to simulation itself. Of course, it also affects how you gather real-world data. And typically, you approach that in a sort of a combined fashion, both with a top-down approach, where typically you have a functional scenario tree, and you try to think about all possible different operational design domains. You break it down, you try to make sure that you have enough coverage, and then you gather pair simulation data there. And then from the bottom up, and that's again where foundation models can help, because through embeddings, they allow you to, for example, label operational design domains where your policies not perform well, thereby forcing you to gather more data to characterize what that failure mode is and then test on it. Again, this is also something we discussed at length in the workshop that I mentioned in March, and we can discuss more about it offline. But here the idea was assuming that we have a good understanding of how to sample the target real domain, how we can get away with less samples by pairing those with simulation.
All right, so for the sake of time, I think unfortunately we have to move on.
Mute and select here laser here. Yeah. So microphone default and okay. Let me try something.
It is headphones, so it will go through here.
Yeah, can I try to say something?
Hello.
Okay. Sounds good.
Okay.
Okay.
I think it should be good.
Okay. Can you say something? Can you see if I can?
Can you hear me?
Yes, sounds good. Awesome. But it's not sharing. Okay, I think it's... Yeah.
Okay.
Probably. So we need to...
Will you take it away? Stop sharing.
Maybe we can...
Let me set up mirroring over here.
It's working.
Well, yep, it is good enough.
All right. I think we should get started with the next talk. So we have Sagar Manglani, the tech lead of the perception team of Telio, and he will share with us a whole bunch of information on auto annotation with vision language models. So take it away.
Thank you. Hello, everyone. So this presentation is about creating a scalable auto annotation model using local VLMs. And the content that we'll be covering today is a little bit about Telio, what is automated data annotation, why we want to use VLMs, what is the problem with auto annotations, and what are the possible solutions over there. So as per Jensen, physical AI is the next major shift that will happen in our lifetime. However, when you look at these problems of moving big things, humanoid robots are not the ones that will be doing that. Humanoid robots are typically what we think of when we think of physical AI. And the reason we need automation in this industry is because right now, over 90% of the construction firms say that they have a hard time filling up the open positions, and 40% of the workforce is going to retire in the next 6 years. So what Telio does is they modify the existing vehicles with the Telio kits so that these machines can be operated by a remote operator. And one operator is able to control multiple machines, and number 2 and 3 can be autonomous. So this is basically supervised autonomy. Here you will see a demo of an actual job site that we have been operating on since the last year. This is Tomahawk Construction in Florida. And this is the operator sitting in a control station that is at a remote location about 50 miles away from the actual job site. So all of these trucks are being operated by a single operator right now. So let's move on. So robotics has a massive data gap right now. And Telio, since they have deployed at several customers, we are collecting data from these customers to eventually unlock the physical AI part. So to make this data useful, we need to annotate it. So the today's talk is going to focus on how to do automated data annotation with VLMs. So what is automated data annotation? This is a frame from the video that you saw earlier. If I pass this frame into the Quen model, these are the annotations that I can get out of it. It recognizes the dump truck excavator, and there is a small car in the background as well. And you would think that 2D annotations don't really sound very exciting, but then having robust annotations is far more important over here because these annotations can be used in downstream tasks like segmentation. Here is an example of when these prompts, the bounding box prompts are passed on to segment anything to model, and this segmentation can later be used to generate 3D segmentation by combining with depth data. So why do we want to use VLMs? Now, annotating known classes of objects is easy. However, when you have a unique object like this, annotations are hard. This is a solar panel powering a computer in the backend, and that is connected to a mast over here, which has a radio on the top. And this whole thing is basically like a trailer. So this is where we can use the power of VLMs by using a prompt like solar trailer tower. And this is what we get out of it. And you can see it recognizes the object fairly well, but you'll notice there are some problems in this video. So you would see examples like where part of the object is selected, either the vehicle frame is selected or the entire frame itself is does the bounding box. So how do we identify the bad annotations? Since we are trying to do video annotations over here, we can use the temporal data to do tracking of the bounding box. And if we observe a sudden change sudden change in the location of the bounding box or of the size, we can mark that one as something that can potentially be bad. But then if we say that something is bad by thresholding it, how do we set that threshold? Like consider the object on the right over here. A part of the object is outside the bounding box. So how do we reject something like this? So that's where we can again bring in VLMs. We have safe annotations. Uh, if you observe a minimal movement with the bounding box, you can mark that annotation as safe. If there is a lot of movement, those annotations can directly be discarded. But the ones in between can be verified with a VLM. So here is an example of refining these annotations with VLM. Some of the examples that were accepted and some of the rejected examples where the bounding box is going out or if the bounding box is incomplete. So here is the same video after filtering and making it pass through the SAM2 pipeline. You can see how the downstream data improves quite a bit by having accurate initial annotations. Similarly, we can see this kind of behavior at night. For example, this is a dump truck driving at night. Now, as it turns around and the light starts flaring in, you will see annotations are going all over the place. And this is the reasoning that we do with a Qwen 2.5 EL model. This is my current favorite model from Alibaba Cloud team, released in March. So it is thinking over the annotations, and eventually it comes out with the response that, no, this is not a good annotation. And by rejecting the bad annotations, here is the kind of output that you can expect out of the model. So we skipped over a bunch of those annotations. The limitations of using this approach are you end up discarding a lot of auto-annotated data. About 1/3 of the data is discarded. The other thing is diverse scenarios are often discarded in these kind of situations. After filtering, we still see around 5% of the frames exhibiting some inconsistencies that would be rejected by a human annotator. And conversely, about 13% of the annotations that were rejected by the VLM actually seem good. So in conclusion, VLMs enable us to label new classes. They help us verify the annotations. They help us with improving downstream tasks like 3D object detection, 3D segmentation. And furthermore, performance of the VLMs can be improved with fine-tuning. The numbers that I showed earlier, 5% and 13%, that exact type of data can be used for fine-tuning the model again, and that can substantially improve the model. This is something that you potentially cannot do with a cloud VLM. That's it. Yes,
Just
please.
to move on to some of the spotlight talks. If you are
Oh.
presenting, it would be great if you could come and sit here on the first
We can
row
talk
and line
offline.
up in order of your presentations. And the first spotlight that we will have is of the paper Interleave BLA, Enhancing Robot Manipulation with Interleave Image Text Image Text Instructions.
Yes.
So if you're the author of that paper, please come up to the stage
Thank you.
immediately. And the other papers in the running session, please come line up here on the front row so that we can call you quickly in order.
All right, so in classic lightning talk style, we're going to be pretty strict about the time limits. Hopefully you guys have practiced. And we're going to just do one at a time, 5 minutes on the clock. And we're going to start with Interleave BLA. Take it away.
Okay, I'm honored here to do this presentation on behalf of my friend Chen Xin. And in this work, we introduce Interleave BLA, a flexible and model agnostic paradigm that extends the state of our vision language action models to comprehend interleaved image text instructions. Our method achieves more than a twice improvement in zero-shot generalization compared to text-based VLA models. Let's begin with the motivation part. Existing VLA models like OpenVLA and Pi0 rely on text-only instructions, which lag behind the multimodal advances of vision language models. In real-world robotics, especially in industrial settings, users often give visual references, such as pick up the object look like this, and describing such objects alone is imprecise, whereas the interleaved image text instructions provide a more intuitive, accurate, and flexible way to specify complex tasks. To this end, we present Interleave VLA, a simple yet effective extension to standard VLA models for handling interleaved image and text instructions. But upon conventional VLAs that process visual and textual input sequentially, our approach enables the model to process interleaved image text token sequences without modifying the underlying architecture. The minimal yet powerful change leads to over twice improvement in zero-shot generalization across both simulated and real-world tasks, demonstrating the advantages of learning and acting on interleaved inputs. A key enabler of interleaved VLA is the construction of suitable training data. Given the scarcity of real-world interleaved instruction datasets in robotics. To address this gap, we propose a pipeline for automatically generating large-scale interleaved data using the existing OpenX embodiment collection. The resulting set incorporates data from 11 sources collection, covering a broad spectrum of object types and tasks. Furthermore, Interleave VLA supports a highly flexible human-robot interaction interface, capable of performing a wide range of tasks off the box, without the need for additional fine-tuning. Beyond standard instruction following scenarios, users can input internet source images, even if such images were not seen during training. And also interact through GUI to encounter those objects during training. Remarkably, Interleave VLA can interpret hand-drawn sketches in a zero-shot setting, despite having never seen trained on sketch data. This emergent generalization capabilities underscore the potential of interleaved image text and affirm the effectiveness of Interleave VLA in advancing more adaptable and practical robotic systems. To further information, we encourage you to read the paper and contact the author through the email. Thank you.
Hello, my name is Donggyuri from KAIST. Today I'm going to present our work called Local VLM, a versatile legged locomotion adaptation through vision language grounding. In recent years, legged locomotion researches have been growing extensively, and locomotion mainly make use of two sensing modalities, that is, proprioception and exteroception. However, these two modalities are still lacking of higher level understanding, as the exteroception is typically extracted either from depth images or elevation maps. So recently, language has become one of the alternatives for robot input modality. Several works, including in legged locomotion, have shown great potentials for using LLMs as an orchestra or high-level planner for robots. However, very often we require to communicate with LLMs on the cloud, which greatly hinders real-time field applications. On top of that, calling LLM online is generally unsafe because we may not be able to expect what output can be generated by the LLM. Therefore, we propose a framework where we firstly scale up motion description data for robot locomotion behaviors using an LLM in an offline manner. These motion descriptions are stored in a database without the need of executing it directly on the robot. The idea behind it is that we believe that some instructions can share similar properties with others. For example, in this figure, an instruction such as show me how a rabbit jump may share similarities with your kangaroo in the embedding space. As you can see in the statistics, our method greatly reduced the unexpected behaviors marked as others. After we have this skill set database, then we deploy it in the real world with a more lightweight VLM and where we used Blip 2. Here we propose the mixed precision and fast retriever. Ultimately, we are able to get as high as 80 our deployment. So to demonstrate our work, we trained a style conditioned locomotion with compliance. Here, the goal is to allow the robot to follow certain gait styles while also ensuring robustness. A framework on a quadrupedal robot here on the left over to other embodiments such as humanoid. So that's all my presentation, and feel free to
Hi there, I'm Theo and I'm from Technical University of Darmstadt. And today I'm going to show you take a first step towards making robot foundation models safe. We have all seen the remarkable success of scaling robot foundation models to larger and larger data sets and solving increasingly complex manipulation tasks and seeing some form of generality. However, the safety aspects of these models has been largely neglected right now, currently. So, and this is apparent in this example where we can see that even though the training data was inherently safe, there was no guarantee for safe deployment. So we were asking ourselves the question of how can we ensure safety without any tedious fine-tuning or additional requirement for data in possibly safety critical scenarios. And what we are proposing is a layer that can be put the output of any robot foundation model, which renders any action to be safe while still having the same performance as before. And in order to do that, we built our approach on this cornerstone assumption that domain knowledge is required in order to ensure safety. And in particular, we made the safety aspect explicit by formulating a set of constraints that the model needs to adhere to during deployment. Our method builds on ATACOM, which is a safe control method that unsafe actions towards safe actions with regards to the safety constraints that we have defined before. And this allows us now to formulate several constraints such as workspace constraints, self-collision constraints, or joint limit constraints. But it also enables us to look more towards automatic constraints generation using foundation models, for example, from the vision side. And this is particularly important if we are looking towards changing scenes where like manually designing these constraints can be a tedious process. And in our case, we're looking at segment anything to do 2D instant segmentation of objects within the scene, which enables us to create 3D bounding boxes and in the end do collision avoidance by formulating constraints on that. So we put our system to the test, and what we can see here is that the formerly unsafe pi0 policy is now safely executing its tasks and does not collide, for example, with the table or any obstacles on the way. Quantitatively, we evaluate our approach regarding the task performance and also the safety aspects in terms of collisions with the environment. And what we can see here is that we have no performance decrease when adding our safety layer on top, while remaining safe throughout all of the trajectories. In a second step, we were looking at a much more dynamic task of robot air hockey, where the goal is to hit the puck into the opponent's goal. And here safety is actually crucial for deployment because much higher forces are acting, and this can be hazardous for either the system or its surroundings. To show that our model is agnostic to any policy, we are deploying an octo policy for this task. And again, we see the similar behavior in simulation, that the success rates remain similar by adding the safety layer, but we remain completely safe. And this finally allows us to deploy our system on a real system where we successfully hit the puck into the goal. So this is the team behind this paper, and feel free to check out our webpage and the paper, or come to my poster outside. Thank you.
Hello everyone, my name is Siki, and presenting this work on behalf of all the authors, semantically safe robot manipulation from semantic scene understanding to motion safeguards. In the control literature, there are a lot of tools to guarantee safety, but what are safety in practice? If we have a drone deployed in an unstructured environment, one natural constraint is not running into any obstacles. With the state-of-the-art SLAM system equipped on board of the quadrotor, we can ensure that the drone acquire a geometric understanding of the environment and therefore not crashing into any obstacles that are known ahead of the time. And here we see the quadrotor navigating through different environment without colliding. In this work in particular, we ask the question, how can we ensure safety beyond geometric understanding of the environment? For example, if we ask a robot to pass a cup of water across the desk, then it should understand that the cup of water should not pass right over the laptop to prevent potential spillage and damage to the laptop. So in the computer vision literature, there's a lot of tools available nowadays to enable robot to acquire semantic understanding. For example, knowing what they are, where they are, and the spatial relationships between different objects, and also what objects are relevant for the task. So in this work, we took a step forward and trying to bridge semantic understanding and the reasoning capabilities enabled by a language model to design safety constraints that allow robots to comply with semantically defined constraints beyond geometric understanding. So we have our semantic perception pipeline where we acquire a segmented point cloud from the environment, and then this information is fed into a language model that allows us to kind of determine what is safe, what is not safe. And our work is motivated from scene graphs. And here, for example, the cup over laptop would then be classified as unsafe action by the language model. And based on this geometric knowledge and the semantic understanding, we construct the semantic safety filter, which is designed based on constraint-bearer function in this work. And this is then used to filter out any unsafe actions that would be sent to the robot. And here are some illustrations or demonstrations we had in our kitchen. And here, for example, the robot is prevented by from putting a bottle of water too close to the X, or preventing the robot from placing a pressure can over a heated stove. And lastly, preventing the robot from putting the fork too closely to the power strip to prevent potential electric shock. Yeah, that's all. Thank you.
All right, good morning, everyone. My name is Rohan Banerjee, presenting on behalf of the first author, Krishna Palampali, who couldn't join today. I'll be talking about our work related to human-in-the-loop foundation model failure recovery for robot-assisted bite acquisition. So just a little bit about our problem domain. So we're interested in the problem of actually getting robots to pick up food items from a plate for assisted robotics type applications. And foundation model pipelines are used a lot in state-of-the-art approaches for this domain. And failure, a wide range of failures do tend to happen in this setting as well. So we're actually focused on asking the user who's present for help in order to recover from these failures. But the question that we're interested in is how do we safely decide when to recover from failures while minimizing the burden on users themselves. So now a little bit more about our problem setting. So we're interested in basically acquiring food items from a plate with multiple food items on it. So we're given these RGB images, overhead images of the plate, and we want to select from a number of skill primitives, three primitives in this setting. The foundation model pipeline that we're considering looks like this. So we have, I guess, two GPTO for prompts, one for selecting the food item, and then one for selecting the downstream primitive. So what we do is we actually develop these two types of querying rules, which try to either use instance-dependent assessments of confidence scores across the population of plates of food, or instance-dependent rules that try to estimate success rates and try to estimate the probability of error for the VLM itself. So this is sort of cycling through the different rules. So this is the second rule, which looks at success rate intervals and checks to see whether there's a sufficient degree of overlap between the and the first rule, which is shown here, is actually looking at the whole population of food plates and trying to see whether the model's prediction is either overconfident or underconfident. So we test these querying rules using a set of actually real plate images. So some of them are used to tune the hyperparameters for the querying rules, and others are used for actually evaluating the querying rules to see whether they actually ask for help in situations where they should and don't ask for help in situations where they shouldn't. And I guess what we find is that the type of querying rule that works best, either instance independent or dependent, kind of depends on the actual downstream task itself. So we find that actually the first set of rules does tend to achieve a higher sort of average success rate across the different modules, the two modules in this case, but it has a higher fraction of false positives, so cases where we query where we shouldn't need to. Whereas the second set of rules is a bit more conservative, so it queries a little bit less, but leads to a more balanced querying performance in terms of NMCC, so balancing false positives and false negatives. So for more information about the rules and our work, please check us out at the poster session. Thanks so much.
Cool. Hi, everyone. My name is Arthur. It's my pleasure to present CRUST. I work on scalable mapless navigation with foundation models and counterfactual guidance. Cool. The problem we're interested in is general purpose outdoor navigation where the robot must navigate to a goal given its current location. And this is challenging because you have to adapt to open set entities, appearances, and other factors in the real world. A scalable alternative is mapless navigation, where you use onboard sensing to reason about safe local paths and course routing guides for global planning. However, existing methods, they struggle to generalize to novel factors and are not robust to different forms of perceptual aliasing. And to generalize, they require collecting large-scale robot datasets. In contrast, our method CREST is able to navigate in these open-world settings without these HD maps using just 3 hours of real-world demonstrations as shown in these unseen environments in diverse urban scenes. Our approach is composed of 2 components, taking an RGBD image. First, we distill foundation model priors to a bird's eye view feature map, and then we learn a reward function using negative counterfactuals to guide the reward learning. To break down this bird's eye view feature map, it's composed of 3 layers. First is a layer for the static features in the scene. Second is a layer for dynamic features, and last for the elevation. We first learn RGBD encoder that regresses DynaV2 features as well as completing the depth. Then we use this depth to then lift these features to 3D and before spline them to bird's eye view. Finally, we take segment anything V2 mask and back project them to bird's eye view to get instance mask. And then we use contrastive learning to learn about instances in the scene. Next, to learn these rewards, we make an observation that negative counterfactuals, i.e. counterfactuals that violate navigation constraints, are important for focusing on. And thus we introduce this counterfactual IRL objective and an active learning framework. In our framework, we first gather expert demonstrations and train a reward function. Then we roll out this policy and identify when we underperform or deviate from the expert. Then we ask a human to label negative counterfactuals, which we then use to retrain a reward function. And then we repeat this until our policy agrees with the expert demonstrations. We test this in a variety of seen and unseen urban environments on task of mapless navigation. And in general, we find that we achieve superior performance, requiring 5 times fewer interventions and all of the comparable state-of-the-art baselines. To dive into this more, you can see that geometric-only methods, while able to do things like basic obstacle avoidance, fail to pay attention to semantic terrain awareness. In contrast, terrain-aware and geometric-aware methods are able to reason somewhat about staying on common terrain such as grass and sidewalk, but struggle to pay attention to small features such as curb ramps or rare semantic classes. In contrast, our method is able to deal with all of these, dealing with rare classes, dealing with small changes in elevation that have large traversability differences, all while remaining robust to perceptual aliasing. And furthermore, we do some experiments that enhance the safety with multimodal learning. Here showing the performance benefits you get to be robust to things like lens flares if you just add in LiDAR in combination with your foundation model features. If you're interested in checking out more about our work, please scan this QR code to check out our paper and website. And you can also find a full uncut video of us navigating 2 kilometers with just 1 human intervention. Yeah.
It's the spotlight talks. We're now going to transition into the poster section, which is going to happen right outside here. The poster section has the posters for all the papers from the entire workshop. So even if you are not able to talk all the posters and all the talks that happened just now, you'll be able to see these posters and talk to the author in the afternoon poster session as well. We're going to be back here at 11 for the oral presentations of the paper submission. So please be back here by 11 and go address some coffee.
All right, cool. Yeah, so I don't need to explain to this audience what an exciting time it is to be working in robotics. And I'd say generally that excitement is because for the first time, we're seeing signs of life that we can develop a generalist robot policy. And by generalist, I mean a robot policy that can be instructed on the fly via natural language to perform many different tasks in many different environments. We see a lot of excitement from industry in this regard with Google and the RTX models, as well as the recently developed Gemini robotics program. We have physical intelligence with their Pi Zero VLA models, TRI with the large behavior models, as well as a lot of work from NVIDIA. And if we take a step back and consider what is actually driving this development, I would argue that there's 2 main considerations that is really pushing the research in this field. The first is the scale of the robot data. Previously, the collection of robot data has been a bottleneck in training robot policies, but with the introduction of large-scale open source data sets like the OpenX embodiment, that bottleneck is starting to be alleviated. In addition, we see leveraging foundation models for robotic control is increasing in popularity. For example, the RTX models, they leverage a VLM and then directly fine-tune it on robot action data to produce a VLA, which is capable of ingesting an observation as well as a language instruction to output robot actions. We have what was followed with OpenVLA, where rather than taking a VLM, they stitched together an LLM, some pre-trained vision encoders, and then fine-tune all of that to produce a VLA that can output robot actions. And then, like most recently, from physical intelligence, we see leveraging like Polygemma, which is a VLM, and then we stitched a small transformer on the side and then fine-tune that to produce these robot actions. And yeah, the key point here is we're leveraging these pre-trained foundation models that are trained on internet scale data, and it's enabling very impressive robot control. And what's really impressive is like out of the box, these work pretty well. This was me running Octo on the WidowX arm in our lab, out of the box, no fine tuning. I just set up the camera how they told me to, and it worked out of the, right away on this task of like putting the carrot on the plate. And yeah, this was incredibly impressive to me. However, there are still like some fundamental limitations when it comes to deploying these policies. Notably, if I just put a few objects on the counter and ask the policy to do the same task from the same initial condition, I can reliably make the policy fail. And I want to highlight that these distractions are what I'm calling task irrelevant, in the sense that they don't change the inherent task difficulty at all. They're just there to distract the policy from the actual object, being the carrot. Now you could say Octo is a rather small model, so what happens if we scale it up? We generally know if we scale the model, performance gets better. And so Octo is about 93 million parameters. So what if we go to OpenVLA, which is a 7 billion parameter model? We can do the same thing with this eggplant task, but then if we run the same policy from the same initial conditions, we again can reliably break the policy. So at the time of this paper, these were the only two VLAs that I could get my hands on, but since then, Pi0 model has been released, which is incredibly impressive. And you can see in this video that they released that the model obviously has the capability of like picking up this hamper. But when you put it in a new environment, the background looks different, there's different objects. Then you see the same hamper on the left and you ask the policy to pick it up. It launches it across the room, which is a safety failure that we would like to avoid. And so while Pi0 is slightly smaller than OpenVLA, it was trained on much more data. And so the takeaway is that this generalization problem is hard across data and model scales. And so we'd like to try and ask ourselves, what can we do to improve generalization? And I'd say there's roughly like two main approaches people try and take. There's what I would call the offline approach, which says, okay, like maybe we can collect more data, try and do some research on algorithms, scale up the architecture, retrain, and just run this loop and repeat. On the other hand, we could ask ourselves, what can we do online? So we keep the model fixed and just try and intervene on either the model itself or the inputs to the model to try and improve performance. And this will be what I'm talking about today. In particular, our method, which we're calling Bring Your Own VLA, is a method that will attempt to perform online interventions on the input observations to try and make the policy more robust. So in particular, if the world's going to give us this observation here, and perhaps the VLA is brittle to these distractions, then we'll change the observation somehow such that the VLA is now robust. And before I talk about the specific details of the method, I just want to like plant a flag and make sure we're all on the same page about what I mean by generalization and what I mean about distractions. So in a broad sense, generalization just means the ability to perform in a scenario that I didn't explicitly see during training. So with our running example from before, if I had this carrot on the plate task, then perhaps like with these objects, the model didn't see this exact scenario. And so we'd want the model to perform well. And in this case, I'm going to refer to these objects as object distractions. I'm calling them object distractions because the robot could like physically manipulate them if it so chooses. On the other hand, we could say that this observation is also something that we hope our model would generalize to, in the sense that this yellow background is something the model probably did not see during training. So what kind of quantitative hit do we take by introducing these distractions? So if Octo, without the object or background distractions, had about a 67% success rate, the performance significantly drops just by adding a few of these task-irrelevant details into the image. OpenVLA, while it is much larger, it also suffers a performance hit when you add some distractions. And so, yeah, we would really like to try and retain the nominal success rate. And that's exactly what our method will attempt to do. So again, just the high-level idea, we're going to take the observation, change it somehow such that the model is now more robust. And the goals for the method are, we want them to be done all online. We want it to be relatively fast and also model agnostic, because sometimes you don't have access to the model weights right away. And so the idea is, and motivation is pretty simple. I would argue a robust model ought to be insensitive to these task-irrelevant details. And so the high-level idea is, if we're sensitive to those task-relevant details, then we'll just transform them somehow such that we're no longer sensitive. It's a simple idea, and the approach is arguably more simple. The first step is we're going to identify what is task-relevant in the image. So if this observation and instruction is put the corn in the pan, I'm just going to query a VLM to ask it what's task-relevant, and it will give me a list of strings that I can use. So things like the sink bottle and also the yellow wall. Given that I now have this list of task-relevant items, I then am going to pass it to a grounded segmentation model. We use grounded SAM2 to localize these regions at the pixel level. And again, I'm going to distinguish between object and background distractions. And the second step is to say, okay, is the model actually sensitive to these regions? And again, we're going to do something incredibly simple. So if this is the nominal observation, we're going to pass this into our VLA model, and it's going to give us output action A. We're then going to take one of the regions, say the yellow background, and we're going to perturb it somehow. In this example, I hope you can see we're using Gaussian noise, but you could use any kind of perturbation that you so choose. And then we're going to pass that into the model, and it's going to give us action A tilde. And then to say, if we're sensitive to it, we're just going to look at the difference between those two actions. And this difference metric D, it's essentially a hyperparameter. We use a weighted L2 distance, but you couldn't essentially use whatever you'd like. And then we're going to repeat this process for all the objects in the image from step 1. And if you visualize like the sensitivity, you can construct this sort of heat map. And then we have a user-defined threshold tau, which says, okay, if we're above tau, the model is sensitive to that. And if we're below it, then we're not sensitive to it. And the regions that are above tau, we're going to inpaint, where if it's an object, we're going to just totally remove it from the object. And if it's a background, we're going to color it such that the model is no longer sensitive to that in-painted color. So it's pretty simple. There's no training going on here. This is just leveraging pre-trained models at runtime. But if you do this simple scheme, then you do the sensitivity approach again, you can see that we're no longer that sensitive to anything in the image anymore. And why does this seem to work? I don't have any good theoretical reason, but the idea is we're trying to bring any kind of out of distribution observation back into distribution so that the model can perform well. And if you look at the training data, it's often trained with distractions as part of the observation. So banana and green cloth, this fork and this pot are distractions for the model. And you can repeat this exercise for a lot of the observations in the OpenX data set. And so then the idea is we have some observation like this at runtime. We want to try and bring it back to the training distribution in hopes that the model is now less robust or more robust to it. So here you can see our model in action. This is Octo. Because we're using action chunking, that's why it kind of looks like it jumps frames. But we run this at runtime for each observation before we query for new actions. And you can see that the model is sensitive to different objects at different points throughout the trajectory. I promised that it was model agnostic. At the time, the other BLA I could use was OpenVLA, and you can see it operating here and performing well. And so if we compare it back to our success chart from before, if we took a performance hit with distractions, with bring your own VLA, we were able to regain most of the performance at runtime, which was nice to see. So yeah, that is our method, bring your own VLA. I'd like to kind of conclude with some limitations and some future work. So on one case, there is the runtime hit that you incur from doing this method. Obviously, in robotics, we want things to be done very quickly, but sometimes if it's safety critical, maybe we don't care about the runtime hit. I think Thomas showed us the Gemini robotics example from earlier where we dropped the pot. Maybe we care a lot about having the pot smash on the ground. And so the 2-second runtime observation intervention that we do is something that we don't necessarily care about. Because I'm not using training at all, I rely on these different foundation models to all orchestrate together well for our method to work. And that's something that is definitely a current limitation. And I'm also really limited to what is task relevant. These objects are very, very distinct, and it's obvious that like they don't pertain to the task. But if you scale to more complex tasks, then what exactly is task relevant may become a bit ambiguous. Yeah, and looking ahead, I think there's many other like runtime approaches that could be used to improve generalization, and some of them have been introduced by people in this room. So some of the latent space safety ideas from Andrea's lab, I think are really interesting and could be perhaps used in conjunction with something like this. Some of the anomaly detection with embedding. So perhaps you could run something like this before you run bring your own VLA and try and have this dual runtime approach to really improve performance. So yeah, and also like the first talk mentioned, there's paradigm shift between like training time compute and also test time compute. And I think kind of looking at the test time adaptation in the context of robotics could be really interesting. And with that, yeah, I'd like to conclude my talk. Thank you for listening and happy to take any questions.
All right, we're gonna have our next speaker set up, but we have time for Q&A. So I'm gonna move this over here like this. We're gonna have our next speaker set up while you guys ask questions.
I'm wondering if you consider using this instead of as a runtime supervision policy instead as a data augmentation or and like auto labeling method to increase the diversity of your sample size of your data set at training time.
Yeah, that's a great question. That's actually something we did not consider, and I think it's a very interesting idea. Some other students actually had mentioned that to me at the other poster session. Yeah, I think it's a great idea, but yeah, it's not something we've looked into.
We have time for one more question. Yeah.
Very doing in-painting, so basically taking one piece of the image and painting over that. What about moving objects? I can imagine the bounding box is inside and moving it around. Have you tried that? Do you think that's gonna work?
Yes, so we did not try it. I do anticipate it working. Yeah, I think the motivation for using like the in-painting where we just totally remove it was simple and it worked well. So yeah, we figured may as well run with it.
We're still sort of working on it. Maybe we can do one more question. Maybe I can ask a question then. I was wondering, so you're sort of identifying task irrelevant parts of the image and then replacing those and painting those. Did you see any cases where the task relevant objects were identified? What happens? And that seems like a risk that sometimes you might in-paint over the things that actually matter. You see some drop in success rate that comes with that as well.
Yeah, absolutely. So we have no like filter on top to prevent like removing a task relevant object. So for example, the caret in plate task, if the VLM said the caret's irrelevant and we totally remove that, then the policy probably has no idea what to do. I did see a few cases of that, and yeah, the policy definitely broke if you remove that object the way that we go around it was we few shot prompted the VLM with some examples, and it normally didn't fail, but the tasks that we considered were pretty simple. So
Speaker one more time. Thank you so much. I think you're good.
Thank you. So while our workforce and the larger nuclear industry's workforce is very capable, they're quite advanced in their knowledge of machining, chemistry, material science, and more, these end users aren't typically proficient at controlling complex systems like robots. And for that reason, we're interested in how language can be used as a control modality for these use cases. And it's worth reiterating that the environments and tasks our group is considered interested in are high stakes. They often involve putting humans in proximity of hazardous materials. And for that reason, it's important to draw this distinction that most of the open data sets that I'll be discussing here prioritize domains that are different from what we're interested in. I've included an image of Rosie the robot here because I associate these kinds of task spaces with domestic labor, like cooking food, folding laundry, fetching objects from around the house. And although there are shared action primitives between these two different domains, they aren't exactly the same. But we've learned recently from these paradigms of scale, both on a model level and data set level, that this isn't a disqualifying domain gap and that there's still potential uses of these data sets for our task space. To be safe and secure in developing our future systems, we know that we must know what is in our data. And to do so, we had to perform this exploratory data analysis. Not just for the safety and security, though, because it can provide additional insights. So first, by characterizing dataset linguistic feature representations, we can identify current spaces that are lacking in instruction following robotics. Second, this work enables us to build some sense of what each dataset can actually support in terms of reasoning tasks and language generalization, which ties into our third point here, that building this improved sense qualitatively, and we show that quantitatively as well, we can build intuition on what kind of data sets might best represent or be included in those future pre-training and fine-tuning mixtures. Fourth, examining the language in the training sets can also help us target next steps in language generalization research in robotics, because you need to know where we're at before we start pushing barriers forward. And lastly, by thoroughly inspecting all of these data sets, not just with automated metrics, but by combing through them, we can identify potential unsafe associations that exist in the data. So the bottom line up front here is that we think that improving language in robotics data sets is low-hanging fruit for all of the reasons listed on this slide. And I'd like to emphasize quickly that this work is still nascent, but I think you will hopefully come to the agreement that these data sets are very repetitive and can be improved upon. So organizationally, the data analysis is broken into a token level and syntax level feature analysis. On the token level, we mostly leverage traditional NLP tools like Spacey, NLTK, Stanford Core NLP packages, things like that. And then for the sentence level analysis, we do automated LLM annotation pipelines to develop those features. And for this talk, we've only considered 7 data sets thus far: Alfred, Bridge v2, Scout, Language Table, RT1, Taco Play, and the Libero benchmark. And of these, 4 are contained in the OpenX embodiment corpus. And why that matters is because even though that corpus was intended for cross-embodiment research, it's quickly becoming the de facto pre-training corpus for VLAs. So we're fully supportive of this effort, but we want to remain clear-eyed about potential deficiencies, not for our own awareness, but also so that we can contribute by improving the language quality in that data set. One of the first experiments we did to build a sense of what is in the data set was a principal component analysis. We used 4 different language encoders. Espert used Sonar Clip to convert this language into embedding representations, and then measured how many principal components are required to account for 95% of the cumulative variance of the data set. So higher number of components is basically a proxy of how much of the embedding space is used, which is a proxy for diversity. GLUE, which is listed first in this chart, is a 7-year-old NLP data set, and it serves as a metric of comparison. We're using these foundation models now developed by the NLP community, and I think it serves as a nice goalpost of future hope, because that data set was developed with the implicit knowledge that your human interlocutor is who you're communicating with, not with a robot. The ordering among robotics data sets from most to least complex is Alfred, Scout, Bridge, Language Table, Taco Play, Libero, and then RT1. And these aren't permanent standings, but they're like general features that emerge from our analysis. So now we'll proceed into the token level work. First, we did an analysis of the unique unigrams. So those are the unique words in each data set. This is basically the vocabulary of each robotics data set. And this is plotted at log scale, just so that we can visualize the robotic data sets at all. And you can see that GLUE dominates here at several orders of magnitude, which follows our PCA work. And it turns out when we did a correlation study between the unigrams present in these data sets and also the PCA component analysis we did, we saw that not only were unique unigrams almost entirely predictive of the embedding space that was covered, but also the size. So the number of trajectories and inherently the repeated language commands associated with each novel trajectory end up being a negative predictor of diversity in the data set. So size does not mean diverse. From a data set collector's point of view, we also considered words and their respective part of speech categories that are shared across these data sets so that you don't potentially hyper-focus on an area of good coverage. For example, soda cans or bags of chips, which are well documented in a lot of these data sets. And those are common noun features that we saw across data sets, and common verb features included picking and placing and moving actions, which is inherent to robotics, but it feels like, again, an easy application of synonym replacement with, even standard or even novel LLM tools to help improve language generalization. So for our syntax level analysis, we wanted to understand the grammatic structures that are present in these data sets, and we use part of speech tagging sequences as a proxy for grammatical categories. So on the right of this chart are language examples from Taco Play and RT1. The part of speech pattern denotes that category, and the sentence column provides 3 different language examples that fit into that grammatical form. So for instance, in the top row, we have put the purple block on the table and slide the yellow block on the table, which are different but belong to the same part of speech category. And we can take this information and visualize it as a part of speech frequency plot. And we can see kind of on the very far right, Taco Play, in yellow, RT1, third from the right, and Libero in the pink in the center, that they're all kind of strongly tailed, and that the most balanced representations across, these are the top 30 part of speech categories represented in each of these data sets, are from both Alfred and the Bridge data set. So if you choose an alternate view of this data, and I don't expect you guys to be able to see much here, but basically what you're trying to see is overlapping coverage of part of speech patterns. And that's helpful to potential data set collectors and people who want to develop pre-training mixtures, because you can see what combination of data sets gives you the best coverage of the grammatic structures you might be interested in. Another area of interest was understanding how many unique task verbs are associated with direct objects. So the direct objects are basically the props that you're using in your manipulation data sets. So bags of chips, cans, boxes, cubes. And the verb count is the unique ways that you can reference interaction with that object, either through synonymous language choice or the actions you choose that are actually semantically distinct. And unsurprisingly, these are also highly tailed, not just because you know, you are limited in the attention and effort you can put into your data set collection, and naturally you might interact with more objects more frequently, but also because there are limitations to doing any sort of contact manipulation tasks with objects. So our recommendation is you can still incorporate non-contact tasks and have equally interesting language commands to ground your actions with, like using negation, which we'll talk to later, or telling a robot to just stop or observe or survey or take a picture or record a feature information about an object. So this is just zooming in to that same plot here to show the most common direct objects and verb relationships in these different data sets. And you can see that there are only like 4 or so unique verbs associated with the objects in the RT1 data set, which is quite large. But clobbering over that to see Alfred, we can see that it's far more balanced and has a greater magnitude of different diverse representations as well. Finally, we investigate the command structure used in language data sets, and it's relevant to understand what kind of task reasoning and planning that each data set supports. So we used a series of heuristics on top of the language features we previously collected to understand the presence of negation, cyclical relationships, conditional action planning, and multi-step task planning. And you can see here, unsurprisingly, that multi-step task planning is the most considered. So another way to potentially increase your language diversity in data sets is to just have more interesting task planning problems where you hinge on incorporating logical features and reasoning to your problem space. So in conclusion, we find that the majority of the explored data sets are repetitive and have poor linguistic coverage. Some of the most diverse data sets, Alfred and Scout, are not part of the OpenX embodiment corpus. But as language currently exists, we worry that VLAs may not be capable of robustly generalizing, linguistically at least, despite the fact that they leverage incredibly powerful LLM backbones in their modeling. So future work is largely focused on completing this data analysis for the complete OpenX embodiment data set. And limitations, obviously, we've only looked at 7 thus far, and we're using automated methods. So eventually we're going to incorporate a formal study of interannotator agreement on the LLM described features of the language used to validate this finding. So I'll take some questions, but for some silly fun, here are some unsafe associations we discovered in the Alfred data set. One where they put a metal knife in a microwave, and another where they stab a metal knife through a wooden table.
Fantastic. All right. So while we get our next speaker set up online, we're going to come up and start using your computer, but you should move that microphone a little bit to the side, and it's time for questions.
Raise your hand and I'll come around to you.
So you mentioned that you were going to explore more data sets in the future. Do you anticipate that those will actually provide anything different from what you've seen before? Or is it more just like the scientific analysis that needs to happen to draw a final conclusion?
The latter is how I feel. I feel like Alfred and Bridge were probably our best bets, followed by language table, and thus far we haven't seen a whole lot of promise from them. There is an additional area of research that I think that this community needs to talk to, and those are those that work with human-robot interaction and social robots more generally. I expect dialogue data sets to have greater language diversity in them, and it's just not something that these two communities are talking about.
Our next
By the way, I can't hear you again.
By the challenges of human-aware AI systems. He has served in major leadership roles and been named a fellow of several professional societies like the Association for the Advancement of AI, the American Association for the Advancement of Science, and the ACM. So without further ado, we look very much forward to your talk.
Hi. Thank you all for the invitation. I'm so sorry I am not there in person. I'm pretty sure the loss is all mine. Giving talks on Zoom is essentially doing all the work and not getting any visceral reward of actually seeing people in person. But unfortunately, I just couldn't travel for this right now. So let's see how far we can get with this. So I wanted to talk to you about some work that we've been doing for a while on using LLMs, LRMs, and also VLMs for planning. And I want to specifically make the connection between style versus correctness considerations and how LLMs are actually good for style, but not necessarily good for correctness. And both are important for, robot plans. And so correctness is important for safety. Style is important for like people finding that the robot the trajectories are pleasing, for example, and they are not, they're kind of sticking to human preferences and so on. So that's basically what I'm going to try and do. I actually from automated planning community, and spent most of my time I have spent working on different planning under different kind of system dynamics, model completeness, and optimization metrics. And before I got into this LLM stuff, as I mentioned in the introduction, I was doing work in human AI interaction, and there's actually a monograph on that work on the archive that you might be interested. But getting back to this talk, essentially, I want us to first start thinking about just the points about what is some properties about planning in general, task planning in particular. This crowd obviously knows things like ergodicity of the environment, and in fact, the fact that these are environments where nothing can go wrong, in the sense that the robot can, the agent can always reach from any state to any other state, so it cannot paint itself into a corner. And so ergodic environments are exactly the kind of environments where planning is almost not needed. And keep that in mind, because it turns out actually in many times when people say LLMs are actually able to do planning, they're looking at ergodic environments. Robustness, of course, is the probability that the plan works in, given the distribution of environments that you're going to work in. And the third thing I want to say is, it's a busy slide, I realize, is there is a difference between sort of the correctness and quality of the plan. Quality is sort of more about the style. Quality captures intangibles such as implicit, unstated preferences. So we'll see in a while, for example, that if you ask the robot to get you a fetch you a pair of scissors, and this hulking robot brings the pair of scissors with the pointy end towards you, it is indeed actually satisfying the goal, but probably not to your comfort, because you're probably worried that that thing is going to just poke you. So there are all sorts of implicit constraints about quality. And typically, if you think of traditional robot planning, task planning approaches, it's exactly that part they have struggled with, because you have to write down all sorts of additional constraints about these quality constraints, in addition to the correctness constraints. And one of the funny things we'll find is, while for the traditional planning, traditional planners, correctness was easy to some extent and quality was hard, things change when you start using LLMs, RVLMs for supporting planning. It's the quality that is easy for them, or style that's easy for them, and correctness that's hard for them. In particular, I show this for many times in my talks to people to think in terms of style versus content and form versus factuality in the context of large language models in particular. LLMs, and of course VLMs too, are essentially generative AI systems, and so they sort of capture the distribution of the data that they've been trained on. So style is a distributional property. And LLMs are able to learn this because they have that's exactly why they've been called the vibe machines. And when I say LLMs, they also mean VLMs. There's a visual, the modality is not making as much of a difference in terms of some of these properties. Correctness and factuality is actually an instance level property. And that's where generative systems in general and LLMs certainly cannot guarantee this, and they can actually fail flat on their face. And correctness is connected to safety. And so you are interested in making sure that that you're aware of these limitations. Civilizationally, humans have always thought style is harder than content, and even traditional planning systems, for example, thought that correctness is easier than getting style correct. But it turns out the LLMs actually shift that argument on its head. One other thing that is worthwhile keeping in mind, I don't want to go into all the details here, is when you're thinking about LLMs, there are certain bad metaphors that you should avoid. Computational complexity of the underlying task has no bearing on how LLMs will guess the solution for that problem. It's not like if you give a prompt, one prompt which is constant time problem, another prompt that corresponds to a semi-decidable problem, standard LLMs not going to think a little bit more for a semi-decidable problem. They start actually outputting tokens in constant time. So corollary basically is that, in fact, this is actually a useful thing for robotics too, that the usual problem characteristics such as stochasticity, partial observability, etc., that made planning environments considerably harder, at least the way we saw traditionally, those don't matter in terms of LLM's ability to guess. They're no better or worse in the correctness of the plans that they guess, irrespective of whether the underlying environment is stochastic or deterministic, etc. Then the other thing on the positive side, they're just amazing amount of background knowledge. They have lots and amount of background knowledge that's been built in because they've been trained on our digital footprints. And so because of which they're very good with no guarantees at capturing common sense, capturing domain knowledge, capturing theory of mind, capturing analogies too. And this is part of the reason why they capture style so well. So that's worthwhile in keeping in mind. It's clear, most of you obviously are aware of the fact that we basically have a bit of, even within the LLMs, we have the standard LLMs, and basically, which are just autoregressively trained on the web corpora, and inference time just complete the prompt. And then the reasoning models, which we'll talk a little bit more about too here, which are the ones that are coming out more recently, starting in last September, O1, R1, and what have been called the long COT models. These are standard LLMs plus two important ideas, test time scaling and post-training. Test time scaling actually is best understood as using LLMs as generators and having verifiers in the loop to keep giving feedback to the LLMs when their generations are wrong. And when you take the same test time scaling technique and actually do it in the training time to solve a huge number of synthetic data problems, and then fine-tune the LLM on those synthetic data problems along with potentially the derivational traces, then you have post-training approaches, which has been the intermediate, the new LLMs, which intermediate tokens that tend to be more correct compared to standard LLMs. So when we're thinking about the properties of LLMs for planning, in general LLMs, and also to some extent LRMs, the standard LLMs are really more like system ones, and the LRMs, the large reasoning models, basically are trying to put in some amount of system 2 capabilities. And so upfront, you shouldn't be surprised that the standard LLMs are actually pretty bad at guaranteeing correctness of plans. And so the foreshadowed summary of this talk, I don't really know how much of it I will get into the details, but I want to give you an idea as to the kind of lessons that we have learned in our work, that LLMs trained just on web corpora are known to have severe limitations on planning and reasoning tasks. So basically, I'll show you in a minute, but that even simple, very simple planning tasks, the good old block stacking kind of task planning tasks, LLMs actually have very bad accuracy. And when they do improve accuracy, if you change the names of the objects, they fall down again, even though the domain hasn't changed, just the names have been changed. But on the other hand, they're actually very good arbiters of style. In fact, that's one of the things, I guess, the organizers for this workshop probably got interested because we've done some work with VLMs in actually critiquing the behavior of robots. That would be the kind of thing where you can have the VLM show give you criticism such as don't give a pair of scissors with a pointy end towards the human, even if in fact that was never actually made part of the problem specification. On the other hand, LLMs, even standard LLMs, can be used as generators in a generate test cycle to give robust planning performance. And LLM modulo is a technique, that is a framework that we've been pushing that basically looks at a large language model as a generator sitting in the middle and generating different hypotheses about plans, which are then subjected to different kinds of criticism by a bank of critics. And then the ones that whenever there is a plan is failing, there is a back prompting to the LLM saying, try again, here is some problems with your plan. And to the extent this loop ends, it's a basically you will get a plan out that actually satisfies all the critiques considerations. So there's actually guarantees about correctness there. And if you are now going from LLM modulo, basically LLM modulo can already be thought of as a special case of what has been called test time scaling techniques in the reasoning large language models. That means you're doing an additional inference at the inference time. But if you push this into the generation time, essentially, if you give yourself a huge number of synthetic data and try to solve them using LLM modulo or some other techniques, and then actually use those traces to further fine-tune the model, then you have essentially what DeepSeek R1 is doing, except in a very large scale. And that's where we currently are. And so the resulting LLMs do have a better correctness guarantees, not as good as the standard planners, for example, but they certainly have better correctness guarantees. And there are a bunch of issues even on the reasoning models about the things like intermediate tokens being seen as reasoning traces that may or may not be relevant to this talk, but I just want to mention that there. So now coming back to some more details of what I already said as the overview of the talk, LLMs cannot plan. We have work in terms of generating correct plans. So if you take something like Block's World and essentially ask in the usual strip style planning problem, saying, here's the configuration, put this, blocks in this other configuration, you would think that's the planning problem that people used to laugh at. The question is, can LLMs do them? And we have a series of papers in Europe's 23, basically showing essentially they couldn't solve them. They're very bad empirically. And then even if, in fact, as later generations of LLMs, standard LLMs are trying to solve these problems, you could show that if you kind of obfuscate the domain by essentially changing the names in the domain, instead of saying pick up a block, you say attack an object. Instead of saying unstack a block from the top of another block, you say feast object from another object, where these other words could either be English words or can be random strings. And they're basically the same dynamics for the domain model, and yet LLMs die specifically in solving this problem. So if you look at that colored table, the blocks world, you see a general increase as the generations of standard LLMs improved, but the mystery blocks world, which is this obfuscated one, basically stays pretty much at 0 and a 3%, 5% level. Apparently, we played too much with the blocks world that essentially, if you ask my name, you get blocks world as a part of the results as an image. Anyway, so the other part, of course, is the chain of thought, react, fine tuning, etc. Don't change the equation that much. We have actually papers on this. There's a NeurIPS 24 paper on chain of thoughtlessness, and the TMLR 2025 paper on the brittleness of React style prompting that you can look up. Basically, what happens in these cases essentially is you can fine tune to or provide these chains of thought to essentially get the LLM compiles the correct solutions for a certain length of the solution, but as the size of the problem increases or the length of the problem increases, the correctness starts falling. This is true in planning, as you can see in the top three curves, but also true in something as simple as last letter concatenation, for those of you who know that very silly problem, where you're essentially taking n words and taking the last letters of each of these words and making a string. And even that, as the number of words increase, the performance falls down. These are all for standard LLMs. Now, having said this, the question would be, why is it that, even this is before September 4, when reasoning model started, why is it that everybody was saying LLMs can do planning? There are lots and lots of papers on this. Well, the interesting thing is, it's kind of worth understanding what are the aspects that what are the computational aspects of what we call planning problems, and what are LLMs good at doing. In general, planning involves having the knowledge about the domain, the actions, the preconditions, general recipes, the old examples, and the generation ability, which involves in particular dealing with interactions between sub-goals and the ability to merge separately generated plans, etc., which become very important in non-ergodic domains, because multiple goals may not, if you can do all goals, any set of goals without ever having to backtrack, then that is the kind of domain where you can show that first of all, be ergodic, and secondly, you barely need planning because you can actually blunder your way through the world just doing something, because you will never get into corners, paint yourself into corners. Comparing that, the aspects of the planning to what LLMs and traditional planners do, traditional planners actually assume that the domain models are given and focus on the search and the interaction resolution. LLMs are actually very good at having domain models almost built in, because they've looked at approximate domain models built in the sense that they have looked at the entire world of data that they've been trained on, but they're actually very bad at doing the interaction resolution. To actually make a point about this, in the NeurIPS 23 paper, we take blocks world and remove the preconditions and the delete list, delete effects and the preconditions of the actions. Once you do that, actions can never get into each other's way. And so you will no longer have sub-goal interactions. And as you keep removing delete and preconditions together in particular, you'll see that the green part increases and the red part reduces. So that sort of tells you that LLMs are actually good at doing planning when planning is not that important. In the sense, interaction resolution is not that important. So if you want to argue that LLMs can plan, you can pick a domain with high branching factor of unenumerated actions, where the interactions are very low. This would be things like 20 questions to guess what someone is thinking, or household or web tasks, or an ergodic world, especially household simulators. In fact, the ability to come up with new actions that you may not have thought about is something that people get very impressed with LLMs, because in traditional planners, you would have to write down the domain model. LLMs are actually good at this quote unquote MacGyver planning, kind of finding some arbitrary way of achieving some sub-goal, but they don't necessarily know that when they're achieving that, whether it will interact with some other sub-goals, handling some other sub-goal. If on the other hand, so you want to argue that LLMs cannot plan, pick a domain with few enumerated actions, but the action interactions are non-trivial, which is pretty much most domains studied in planning, RL, planning and reinforcement learning, blocks world, logistics, travel planning with constraints, etc. And robotics falls right in the middle. It has some aspects of, I should be able to do things even for which there are no recipes. And there's also aspects of you better be safe and don't paint yourself into the corner. That's why you have to know what LLMs can and cannot do. They're actually very good at, as I said, approximate knowledge sources. And so you can actually use LLMs and derive domain models from them that can be used to feed to traditional planners. If you are interested in doing that, we have work on that in NeurIPS. The second part that I want to make now is, if you go from standard LLMs, which have these problems, and you want to get into giving them higher reasoning powers, that is basically provide more correctness guarantees on the planning. How do we basically go from system 1 LLMs to system 1+2 LRMs? Basic idea is the first idea, that is test time scaling, which basically brings back system 2 ideas into system 1 by essentially thinking of LLMs as a generator of ideas, and then some additional, so instead of just generating one idea and stopping, you can have, for example, a very simplistic thing would be let LLM generate multiple plans and then some critique kind of picks among them, kind of ranks them and picks the best. That's sort of the poor man's approach for test time scaling. A much better approach, which actually we call LLM modulo, that I'll talk in a minute, is essentially you have the LLM generate a plan and you have a bank of verifiers. Some of them are formal verifiers, some of them are learned verifiers, some of them are code synthesized verifiers, and some of them are LLMs themselves, which can actually just do style critiquing, and then these critiques will then give suggestions back to LLM until there is sort of an equilibrium, and then basically something that satisfies most critiques concerns is actually sent out. So that's what we called LLM modulo. There's a position paper as well as lots of arguments on this in ICML 2024, which by the way they actually gave a tutorial on all this stuff in ICML2 that's available on the web in case you're interested. So basically, as I said, large language models, LLM, even though I started with LLM, actually we'll say towards the end that you could actually replace the LLM with LRM, which is one of the new reasoning models like the O1 or DeepSeek R1, and can still improve their accuracy with now guarantees. So basically, the critiques can be, as I said, different types of critiques, and there is sort of a generate test interaction going back and forth between them. And there are multiple critiques. And one other thing I want to mention is in robotics in particular, lots of people have actually looked at somehow taking the planning description, converting it to, let's say, some formal description like PDDL or something, and giving it to a planner so that it'll actually solve that problem. There is also, instead of PDDL, you can actually convert to SMT's specification and give it to an SMT solver. I'm generally less interested in having solvers than verifiers. You can think of solvers as really verifiers plus search. And LLMs are already generators, so you can do generate test kind of a search with a bank of verifiers. And the verifiers are composable. So you have additional constraints. You can throw in new kinds of verifiers into this bank, and they will start actually dealing with new kinds of constraints. Whereas solvers come for specific subsets of constraints of the big bad problem. There are classical planners, there are temporal planners, there are stochastic planners, etc. You basically have to pick the right solver to begin with, whereas here you can just mix and match. And the soundness actually of the plans coming out depends on essentially the verifiers guarantees. If the verifiers are guaranteeing that the solution is correct, then it's essentially sound with respect to the verifiers. The completeness depends on the LLM's ability to generate a diverse set of guesses. And that's actually important too, because LLMs don't generate all possible guesses. And so, in fact, if you are following things like Alpha Evolve actually can be thought of as an LLM modulo system where the verifier is essentially the Python interpreter, which can run the code, test it on the unit tests, and then decide whether or not the code is working. And to actually improve the code and come up with different versions of the code, you are actually not only having just LLM, but you also have specific way of diversifying the suggestions that the LLM makes. In their case, they use genetic algorithms for that. So this is basically using LLMs, but with diverse suggestions. So there are different types of critiques in LLM modulo, correctness versus style. LLMs themselves cannot directly critique correctness, but they can be used to critique style. In a minute, I'll mention that and actually show you that VLM work. Critiques can be binary, just say try again, or can be constructive, point out errors in the candidate, or suggest local repairs. And you can have a meta controller combining the order in which the critiques are subjected to the planning. Okay, so it turns out LLMs are not good at self-critiquing in terms of correctness. We have an ICRA paper that shows that when LLMs are made to critique their correctness of the plans, the overall system's performance can go down. That's partly because LLMs might actually walk over a correct solution, giving it a false negative, and then stop at a wrong solution. But on the other hand, you can use LLM in particular VLMs as behavior critiques, and then that's what we did in a Comb paper, where we actually used that to kind of critique the trajectories the robot generates in terms of what you can what might and might not be reasonable with respect to the kinds of trajectories that the models have been trained on. And so that actually, they're actually very good at that hand scissors thing, for example, they're able to capture those sorts of things. You can also do human preferences can be captured to some extent by LLM. So there's an HRI paper that shows how that is also a style constraint, and to some extent, they're brittle, but they can capture some of that to some extent. We are not the only ones mentioning this point. There's actually a paper in ICLR, for example, that says style outweighs substance failure modes of LLM judges in alignment benchmarking. So this is slowly becoming more part of the community understanding. So actually, this sort of a test time scaling with LLM modulo, as I said, kind of can be sought and used to understand alpha geometry, alpha proof kinds of work, as well as program synthesis work too. And it's a way of actually introducing correctness and safety guarantees. So there are so the part which how much time, if any, do I have, Andrea?
If you could please wrap up in the next minute or so, that would be
Okay, fine.
fantastic.
Okay, that I can do this here. So then basically, the second part that actually captures the improvement in the reasoning models is once you have test time scaling, how do you make the generator be better? And that's essentially, as Marvin Minsky said, intelligence is integrating the test part of generate test into the generate part. And so you could do this in a sort of an LLM modular framework where after you solve the problem, you actually can generate synthetic data, which now with the solutions, which can be used to fine tune the model. And you can do this in much larger scale. That's what has been the case with post-training approaches, and they do improve. And in fact, you can think of post-training with test time scaling as sort of slowly increasing the inference horizon for the LLMs, but without full guarantees. So that sort of is the way. I think I'll probably skip over some of the details on how planning works on O1. And then I do want to mention that you could use O1 style systems in the LLM modular framework and actually do better than them in terms of accuracy. And then there's a bunch of thoughts that I can talk to you about in LLMs, especially about the fact that there's a considerable misconceptions about the role of intermediate tokens. And then I want to summarize by bringing back my old part that essentially this style versus correctness distinction can be used as a good way to figure out where LLMs and VLMs are actually usable and where you should be more careful about using them without combining them with test time scaling sorts of techniques. So I will stop there, and I don't know whether questions will work, but if there are questions, I'll take it. Thank you.
Thank you very much. All right, we have time for maybe 1, 2 questions, so we can then break for lunch. Rohan's going to moderate those questions for anyone in the audience.
Please raise your hand. With mic.
I can also kick us off. Maybe I'll start with one question. What is your take on what makes style and correctness unique when you put LLMs into robotics versus style and correctness in a non-embodied context like just LLMs?
So what I kept thinking, based in terms of especially the way VLMs have been used in robotics foundation models, is most of the time they are being used to get the right kind of trajectories. It's not a question of stopping failure, but if I'm trying to reach a point here, I can go like this or go more smoothly like this. And getting those kinds of smoother trajectories, it's like a better style consideration as against stopping, bumping into things. That becomes a more correctness consideration. In a continuous space with so many different decisions to be made in terms of actually figuring out how the trajectory is being generated, VLMs wind up being very good sources of giving a good style approach, which then you can check for correctness in terms of is it actually jumping into things and so on. So in a way, I actually always thought that the reason, in some sense, planning started between robotics and automated planning communities used to be, and even to some extent now are kind of close enough, but they kind of drifted partly because the robotics people would actually care about the continuous trajectories and making sure that those trajectories are generated before actually thinking about the correctness guarantees. And so that part actually VLMs and LLMs could be quite useful. And that might be one reason why people are more excited. But there are also people in robotics who are also looking at things like correctness considerations with this SMT style compilation into SMT solvers and so on.
Got it. Thank you. Any other questions from the audience? All right, I think we're going to wrap that up then, and we're going to break for lunch. Thank you very much for your talk. Let's thank the speaker one more time.
Thank you.
Fantastic. So now we're going to break for lunch. We have an hour, so we're back here at 1 o'clock for our next keynote speaker. It's going to be Mingxing Tan from Waymo, and he's going to tell us about how Waymo is approaching the AV stack in the era of LLMs. And now you can screen share. I hit it. All right, perfect. Wow, smoothest transition. All right, it is my great pleasure to introduce Professor Mark Riedel from Georgia Tech School of Interactive Computing. He's an associate director also of the Georgia Tech Machine Learning Center as well. Mark's research focuses on human-centered artificial intelligence, very, very relevant considering how interactive all of that is these days. And specifically the development of AI and ML technologies that understand and interact with human users in more natural ways. Mark's recent work has focused on story understanding and generation, computational creativity, explainable AI, and teaching virtual agents to behave safely. Mark has won numerous awards, including the NSF Career Award, DARPA, ONR, US Army, et cetera, et cetera, et cetera. But I think it's time to pause and turn over the floor. Go ahead.
All right, thank you so much. So I'm very fortunate to have a job where I get to kind of do whatever the hell I want, as you can kind of hear from the bio here. And so I started looking at safe AI systems maybe as early as 2015 in virtual agents, long before we had VLMs and all sorts of fancy large language models and things like that. Somewhere along the way, I got interested in explainable AI. And then Andrea and the organizers come and said, why don't you talk here about XAI at a safety conference? It's like, what do I talk about? And then I started to realize, and it's thanks to you, that there was actually some common themes that were running through my research. I'm going to try to pull those out today and kind of talk about how some of the safety alignment, larger term projects that the community has been looking at and explainable AI actually sort of linked together in interesting sorts of ways. Before I really get into things, I have a few admissions that I have to make. First of all, I'm not a roboticist. This is my robot in my lab. And this is all you're thinking right now. It's like, grr, not a roboticist. What are you doing here? Second of all, there's no VLMs in this talk. Grr. Okay, all right. And this is ultimately a reinforcement learning talk. And I understand there's a complex relationship between reinforcement learning and robotics. So of course, I should just see myself out at this point. Okay, but I do think maybe I'll have some if nothing else, entertaining things to talk about. Okay, but I do kind of want to set a little bit of a frame here. You know, a lot of the community is interested in this thing called value alignment. What is value alignment? Well, very writ large is the property of intelligent agents, indicating that they can only pursue objectives and activities that are beneficial to humans. And of course, that brings up a lot of questions. But what we really want to know is, are our AI systems values aligned with their values and vice versa? And that is important because we are dealing with, in lots of cases, especially with large language models, but in all sorts of sophisticated, complicated agents in complicated environments, what's called the incomplete objective, which is that when we talk to an AI system, whatever happens to be, we often tell it that we want something, some objective to be met. And to us, it's very clear how that should be done and what should actually be done, but not always to the AI system, because we often leave out some of the most important details, which is, you know, when I want you to do this thing, I want you to do it in a safe way. I want you to do it somewhat how I'm thinking about you doing it. I want you to be doing it in the most helpful way, and so on and so forth. So there's all these unspoken parts of the objective of the which involves constraints about what not to do, preferences for what to do. And so really value alignment kind of boils down to something that's a little bit more understandable, which is that we have a preference over the space of solution behaviors for our agents, robots, whatever they happen to be. Now, the way I've been thinking about, and there's lots of different ways to approach value alignment or preference alignment or whatever happens to be. But I think, you know, as someone who also studies humans and human societies, we do know that we prefer certain behaviors. We as humans prefer certain behaviors, largely because we've learned to emulate an accepted pattern. So why do we stand in line when we're at the cafeteria to get our lunch? Not because we're thinking in some sort of rational senses like, well, you know, there's a fairness issue about them first and they should be served first. We just kind of fall in line because that's just the thing we do. And it's the thing that we've always done as children. But there's actually some importance to this, not just that we've kind of learned from our parents and learned from society, but that social norms, whether it's standing in line or walking on the right side or the left side of the road, or you know, being polite or whatever it happens to be, they exist because there's an implied social contract, and that helps us reduce interpersonal conflict, right? Because we all have expectations that if we all sort of play by the same quote unquote rules, then we will all sort of fall into a comfortable pattern with each other, and we won't kind of rub elbows and get in each other's way and create unnecessary conflict. And so the idea here is that even if AI systems can somehow understand the social norms, and of course, social norms are very different societies, different cultures, different parts of the nation, different parts of the city, so on and so forth. But whatever our system is doing, and that if it falls into line with our expectations, then we will rub elbows less with it. We will run into conflict less. And just to kind of give you an example, because I actually didn't plan this, but the Waymo talk came before me. The other day, riding my bike to campus, I almost rear-ended a Waymo car because it actually stopped at a stop sign. And I was not now, that being said, I love riding in Waymos. I think that's the most enjoyable ride-sharing kind of experience I have. But outside on a bike, you know, I was in this mode of, well, you know, no one ever stops at this obscure stop sign, and it stopped, and I stopped very quickly. Always fine, always good. I'm a data point in a Waymo car database somewhere now. Okay, so social norms, they implicitly encode moral values, but also kind of patterns of behavior that we find acceptable, that we have preferences over. And it's specifically at the action level, like whether we stop or not for a stop sign. And so now the question is, can we build mental models? Can we as humans build mental models of the AI systems behaviors and anticipate and respond accordingly? And can those AI systems build mental models of our social sets of norms and procedures and then act responsibly around us? So this is kind of what we're sort of building for. And as I mentioned, I wanted to put this together with explainable AI. So I started to think about the landscape of how all these things go together. So whenever I get stuck on something, this is sort of what I do. I cross hairs and say, can I kind of break up the world into different sort of ideas? And I'm not sure I'm super convinced by this way of breaking things down, but I'll put it up here anyways. You know, first of all, we have aligning the user. And in this corner, I'm going to say aligning the user with learning. Okay, so this is how humans get to understand how AI or computer systems work. I'm not going to talk about this. This is what's happened since the 1970s. We learn how to use our computer systems. We learn how to talk to Siri successfully because it actually isn't very good with like open-ended conversation, right? So we're always left to learn how to use our tools, and they don't always work the way we want. Okay, so we're going to not talk about that. What we'll talk about, of course, is aligning the agent to social norms, to our behavior preferences, and we'll do that. This is where I'll start the meat of the talk. I put something down here on the bottom. So I'll put XAI, explainable AI systems. And I think that also can also make sense when it comes to aligning the user and aligning the agent. So when it comes to XAI, we usually think about explanations from an AI system to a human as help the human understand what's going on inside the AI system. So you can sort of think about this as aligning the user to the human, not through letting them learn through experience, but let's help tell them what they need to know about the AI system to use it and be successful around it. And then here's where I think we close the loop, right? I think a new way of thinking about explainable AI is, well, can we also use explainable systems to help control the preference space that an agent is operating in? And I think this will be like maybe the new thing that if you're familiar with any of these things, hopefully this will be kind of a new interesting connection. Okay, so let's just kind of work through these things. I'm not going to spend a lot of time on safety alignment, value alignment, or alignment tuning. I do this work in virtual agents. And of course, if we're going to build alignment systems and we want to test value alignment, we need to do this in a safe way in an environment that's complex and real world enough that we can draw some sort of conclusion about this. For me, this is text games. And the most canonical game is Zork, where you type in what you do and it spins out text back to you. So it's a text interaction world. And we've been having agents play these environments for a long time. I think they're really reasonably suited for the task because their space potential outputs is language, so large partially observable space. Their action space is large. There's billions of things to type in. Most of them don't do anything useful, but you can type them in nonetheless. They require common sense reasoning, and they often involve non-player characters or social simulations, social settings, social situations. So they're like little text-based simulations of real-world like situations. So this is the context that I'm going to talk about AI safety agents in there. And to kind of tell you about why this is also a good way of dealing with safety issues and value alignment is because it's really, really easy to set up incomplete objective problems. So we can set up a social simulation in one of these text worlds. Maybe we can have an agent go shopping, and we can environment and figure out how to go shopping. And this is maybe something that would, if you just put a vanilla reinforcement learning agent inside one of these environments. So they learn to go shopping by going to the mall, going into the store, taking some clothes, and going home. Last time I tried to do this, I got arrested. Never tried to do this, but that's probably what would happen. Okay, now, so basically it's really easy to set up situations which agents misbehave because they don't really understand the social context, the social environments, the social norms going around it, right? Now, once we, and most of it because they just don't, reinforcement learners just know what they can know from the interacting with the environment. We put large language models in these reinforcement learning agents, and I'll show you how we might do this in a little bit. They can sometimes learn some of these latent features that are important to us as humans and pull those out and do a little better. So a really kind of standard way of doing this would be to take your standard actor critic, which would normally take some sort of observation, right? Some sort of encoding, get your action, get your value. What we do is we put a language model inside. It's a little bit old, so we're using Albert, which is just a version of BERT, right? We could do better than that if we really wanted to. And then the second thing we do is we actually don't get BERT to tell us what to do. We say, build a representation of the world with maybe some of these latent variables. This model, this graph becomes like a memory repository for the agent that it operates on. And then this also fades into the action choices. So lots of reasons why this kind of works, but one of it is that it does pick up on some of the things that maybe are not immediately useful to the agent, like money. and it does figure out that maybe you should actually give money to the agent to a shop person before you take the clothes, and thus we don't go to jail. Now, it doesn't always do this, whether the reward function is amenable to having extra things like using extra objects and things like that. Sometimes it just learns that it's still faster and more efficient not to pay money, just run for it, right, I guess. So this is not the total answer here. The way that we really, where do we get the social norms into it? Large language models have some of it, right? But how do we get this in? And you really, I think we have to look at it as a reward function learning. It's like, so we have this reward function is incomplete. How can we learn more about the reward function? That was a little bit left unstated. Kind of give you a shallow look before we move on to other things. We tell stories to our agents, and we have those agents decompose the stories and say, what are the important parts of this story that I should pick up and bring into it as, like, in addition to everything that you told me, these things from your story is also really, really important. And to kind of extend the sketch, right? So we're looking at the text, we have memory of what's going on here, but we have the agent also take a story, like, this is the last time I went shopping, I did this, or this is what I often do when I go shopping, this is the sort of story. We pull out the key state elements, which is this is what the world looks like after a story happens, after this idealized experience happens, which is the story. And then we can look and see, are basically these two graphs becoming more similar to each other? And if they are, that becomes reward. And then we can basically learn to build the world that looks more like the outcome story, right? So this is different than learning by demonstration. We're not actions, but we're focused on the state information. And what we're doing is we're pulling out the state information and making it implicit state information explicit. And if we do that, we get a slightly different agent that adds some extra components. So my wife always tells me, this is how I shop. My wife always tells me, that's not how real humans shop. You shop like a robot, right? You never try anything on, right? So if I were to say, can we build an agent that is going to, meet expectations, social clothing and buying, right? I don't know if you ever want a robot to try on clothes, but if you ever did, this is what you'd expect a robot to do. Okay, so I'm not going to spend a whole lot of time on that. What I really wanted to convey, though, was expectations, right? Expectations being the principle in which we can align agent behavior. Okay, so now we're going to turn things around, and we're going to use this notion of expectations, and we're going to switch to explain AI and getting humans to understand how agents operate and behave. So if you haven't come across explainable AI, the idea here is we have some sort of AI system or an agent that generates a recommendation, makes decisions, generates behavior, whatever happens to be. And then a second component provides a justification for those AI outputs. And presumably the idea is that you can take those justifications and use something with those justifications. Information is useful to a user to act on. Now, we're not thinking about this in terms of like a software developer. Like the actionability of an explanation is, oh, I can build my agent better, or I can identify where the errors are happening and I can improve the model, right? Which is one sort of actionability. But we also have an entire other class of users, and it turns out there's more of those than developers, which are everyday people. And they're interacting with AI systems in many, many different ways, including putting cats on Roombas, also writing in Waymos and things like that. And for them, the notion of actionability is different. They're not going to go and change the data, fix the model, update the algorithms when their Roomba kills their cat or whatever happens. For me, it's just they eat the cords. It's really annoying. Can't teach it not to do that. Don't know how. There's probably another talk somewhere in ICRA about this happening right now. All right, but what can we do as if we were to understand what they were doing, why they're doing, how they're working? How can we adapt our behavior to them or help the agents adapt their own behavior? So this is what I kind of want to get at here. And of course, I'm going back to the world of agents. And we all know that agents are sequential decision making. This makes problems especially hard because just look at a particular decision at a particular point, but that decision is usually predicated on future activities that the agent thinks it will do, right? It's looking for future payoffs every time it makes a decision. And of course, we know that at least in agent worlds, games and things like that, reinforcement learning is a really good way of solving reinforcement learning problems, sequential decision-making problems. Okay, so now in reinforcement learning, you can without getting into details, you're basically thinking about an agent trying to reverse engineer the true utility of performing different actions in different states. We call this the Q value. And if we were to look at a very simple world like the one down here, where we have an agent who's trying to get to some goal, there's some stairs, there's some rough floor. The agent's goal is to come up with these utility numbers, right? It could be done with neural or it could be explicit like this, right? But somehow notion that certain actions in certain states are better than others, right? And then once it has to make a decision, it should go to the states that have more utility, better utility, right? So this agent will go up and around there. Now, what does this have to do with explainability? How do we explain a policy like this to a human? Well, here's one way, the most natural way. Action A is the best thing to do in state S because after 10,000 trials, A led to a higher reward than any other actions. Of course I'm going up. Why are you asking, you silly human? That's not particularly useful. I don't know what to do with this. I'm a computer scientist and I don't know what to do with that information. Okay. Now the issue is that when we reverse engineer these utilities, most of our learning algorithms, they just forget why the numbers went up or down. Okay, and because it's forgotten why these numbers go up and down, they can't tell you anything about the numbers. This number's high, this number's low. I don't know why. I did some math, and that's what the math told me. What we really want is something that looks more like this, and counterfactuals explaining why other alternatives are bad are often very actionable, right? So why did you go north? Well, I chose north because if I went south, I might fall down the stairs. Where is fall down the stairs in these numbers here? They're not, right? Somehow there's the notion that these numbers are lower because of that, but we don't really have that explicit understanding. And if we can come up with explanations like this, we might be able to help an agent understand why the agent is doing what it's doing right now, why this chosen behavior is important to the agent. Like, it's really afraid of stairs, okay. Maybe if I, as a bipedal human, I don't worry too much about stairs, but maybe my robot really does because it's different form factor for me. Right now, maybe I can change my mental state. Oh yeah, my robot's afraid of stairs. I need to take that into account when I'm interacting with it. And maybe I can even do something about it. Well, maybe if I put a child gate in front of the stairs, then my agent will take the faster route and I'll get my Coke faster or my coffee faster or whatever happens to be. Okay, so quick sketch about how we might get this these intuitions back into reinforcement learning systems. What we're going to do is we're going to learn how to predict the reward influences on states. So what do I mean by reward influences? Well, every one of these states is in some way influenced by the possibility of achieving other states. Like this green sort of implies like how much you are likely to be close to a goal, right? But some of these states are also influenced by the negative reward that come from stairs. And some of them are influenced by the negative reward coming from rough floors, right? So every one of these states is a combination of influences in terms of how much that state you're likely to interact with these future rewards. Okay, once we can do that, then we can say, all right, there's the way that the agent actually went. There's the way the human wished that the agent went. We'll call that the counterfactual. And then we can look at each of these states and say, well, what's the differences? There's some qualitative difference in terms of the types of influences, the types of rewards that the agent is interacting with up here versus down here. And if we can find those differences and turn them into language, and I won't talk about how that's doing it, but you can kind of get the idea of like, not just say stairs are bad, but the word stairs should be associated with this state. Then we look for those differences and we can convey those differences to the humans, which will give us the explanations like we just saw on the previous slide. Okay. So to get this a little bit more precise, what do these influence predictors do? Is they're basically trying to say, what is the probability of interacting with every possible reward given a particular state, ignoring all the other rewards out there? All right, so if this is the agent's actual policy in a very simple grid world, the idea is the agent has to get over green, and these combinations of yellow, blue, and purple, some of these are bad for the agent, some of them are good for the agent, but we can sort of see like these are probably bad down here. The agent is probably going to want to go up over the top. And we say, well, what is, if we only had to focus on the goal, what would we know about these states? Well, these are the good states, these are the bad states. And if we only had to worry about some of these bad actors down here, whatever they are, right? These are the bad states, these are the good states up here. And it turns out that the actual policy that the agent will learn is approximately the equivalent of multiplying all these things together. And this is about 90% accurate of reconstructing the actual policy. So we learned these in addition to these, and then these influencers become part of creating the explanations because the actual policy has forgotten why this goal is important and why these things are bad. Okay, so not going to go into any more of the detail or the mathematics of that. does this help with our users? In other words, does it help align the users? Does it help the users understand why the agent makes particular choices? Okay, does it change the user's mental model of how agents behave, what agents care about in the environment? And it turns out the more that our participants interact with the agent over a long period of time, like 3 or 4 interactions, that's very long, we see that people who are exposed to our explanations, they tend to get a very good idea, and they're able to predict what the agent will do. Oh yeah, the agent will never do that. It's afraid of this. The agent will prefer these sorts of things. So the humans is basically learning the preference space that the agent has as it's learned to solve the problem, and other explanation types, not so much. And we've done this in grid worlds. We did this in a Minecraft-like environment as well. Okay. Now let me shift to the last thing and say, well, so what? So the humans can, of course, learn to do better, to make mental model predictions of what agents are doing. But let me kind of throw something else out to you, right? I can understand what the agent is doing and why it's doing it. And that was the part 2 of the talk. But what happens when the agent says, I understand why you're doing it, but I'd really rather you do something else? The problem is you're not programmed to do something else. You have your own preferences. I have my preferences. They're not aligned with each other. Well, before we go on, remember that the policy, what the agent is learning, is a function of the environment and reward. So in other words, how the agent thinks about the environment. So if I understand how the agent responds to particular environmental features, environmental cues, to get to a long-term goal, maybe I can just can I change the agent's behavior? Well, sure, if I can change the environment. If I understand how it interacts with the environment, change the agent's behavior. So can we get that out of explanations? How much time do I have? 2 minutes? All right, I'm good. All right, so here's the situation, right? The agent is going to do a particular task. They're going to move through the state space in a particular way. They're going to do some sort of consequential action, AT here. And the human's going to come along and say, you know what? I really wish you had done this other thing instead. Okay? What this really means is the agent will come back and say, well, if you wanted me to do this, I shouldn't have been in that state. I should have been in this state instead. And now it's up to the human to decide, well, can I figure out how it can change the environment to get the agent into this state? Now, I'm not going to go into a lot of the details here, but how we're going to solve this is through something called world models. World models just mean the agent's able to predict its own future states. This is what we usually do, like to train agents really effectively. Agents can predict their own future. What we're asking the agent now to do is predict its own past, because this state is counterfactual. This might be one that might never actually exist or happen. If we don't think about, if I want to be here, I should have come from here. So we reverse the world models, we predict hypothetical pasts, and I won't go into details about how that happens, but by showing the agent, every time you disagree with what I'm doing, I will show you what I thought the world meant to do what you want me to do. And now it's up to the human to figure out, can I make the world look like that? And what we can show is that most people are really, really good once we show these counterfactual backwards states, reverse states, of figuring out exactly what was wrong with the environment. And that's the first step to figuring out what the environment should look like. Okay, so the idea here is help the user, help the agent fall into the user's preference space as opposed to staying within the agent's own space. All right, so I'm going to just kind of try to pull all these 3 threads together now in the last minute I have or so. Human AI interaction, I think that's what we're all interested in here. I'm making the argument that this interaction will be safer when AI agents and humans are in alignment with respect to each other's expectations. So I have an expectation model for you, you have an expectation model for me. We should be more or less in accordance with what we think is going to happen and what we should our joint goals happen. Of course, we know that we can teach agents how to learn social context, learn the social norms. That's what we talked about. My way is not the only way. We can use large language models are actually pretty good at learning how to do these things as well. And we know that we can use explanations to teach humans to have better mental models of the agents. And to close the loop, what I think we have to do more of is have these explanations not just say, here's what my agent wants to do and why, but here is how you can influence me, the agent, if you want me to fall into your preference space. And therein, I think you now have a closed loop of agents, humans aligning their expectations, and then being able to influence each other to bring those expectations closer when they're not in full alignment. All right. Some amazing people have worked with me over the years. This is just a few of them that I would like to give special. I would like to thank all of you listening to my weird non-VLM talk. Hopefully I have questions, and thank you very much.
Fantastic. Thank you so much, Mark. All right, questions. We have, okay, I'm gonna. Oh,
Start with
when
the
there's
easy
two
one.
questions. If you are a spotlight speaker, please come up to the front and line up in your order so we can keep to time. Let's go for questions.
So my question is more philosophical. Why do you want to have AI agents aligned with our values and not rather let AI discover better values and make us better humans?
Oh, that's a good one. Why shouldn't we let them discover new values and make better humans? Because evolution is slow, I think. And there's a sort of a what can we do now versus what can we do later sort of aspect.
Like let's go.
Okay.
So for the when you learn kind of the reasoning behind what happens if it's dynamic? So right now, kind of you're learning, you know, this is where the obstacles are. Here's where the goal is, and kind of those kind of. I would think the main thing about these as potential functions really.
Yeah.
Repulsive and attractive forces. So what happens when it's dynamic?
The environment's dynamic. Yeah, well, there's two types of dynamics. There's in-domain dynamic, which is that you've trained on an environment that's changed. So you're used to changing and you have a generalizable model. My models don't generalize that much because I'm not focusing on that, but there's no other work can, right? The bigger issue is out of distribution changes, which are sometimes called novelties or anomalies or change points. This is like a whole other thesis project, but it does fall in there, right? Because you might want to say my agent is failing because not only its expectations of the human, but its expectations of the environment are wrong. How do we convey that to the human? Because maybe the human has to come in and say, all right, well, you've got to fix this anomaly, this novelty. You need to, how do you return the environment back to distribution so it'll work again? So I do think that you still want to have this same loop, but of course that loop just becomes so much more difficult. Partial answer.
More questions. I have one brief question for
Yes,
you.
please.
So I love reinforcement learning. It's really cool. I think it's the right way to model, you know, agentic interactions.
So at least two of us.
However, there is something to be said about like when you have these really large statistically driven models, something like norms feels like something you should be able to emerge that should be able to emerge from just like a lot of data, maybe. So what's your take on like how some of these kinds of characteristics or aspects of an agent should emerge? Should it be from something just like open loop data collection? I just see a lot of things happen frequently, and this just means this is a norm and I should adhere to it, versus something that's a little bit more encoded by a reward function or something like that?
Yeah, I mean, I think, you know, to get a little bit philosophical here, I think in the perfect world, you'd be able to put reinforcement learners out to trial and error their way through society, the way humans are raised societies. And if you have a large enough, generalizable enough, you know, very large RL model, policy model, you would learn some of this stuff. They would all kind of emerge. Now that data is really, really hard to get. And so this is one of the reasons why I think, you know, we often turn to shortcuts. My shortcut is put the large language model in the middle of the reinforcement learning loop, because it has at least read about society and has a more general, it's usually not grounded, right? So I'm teasing it around this grounding issue, and I'm a virtual agents person because I don't know how to solve the grounding problem. But eventually we do have to bring the grounding and the language models together, or we need to learn in environment. Of course, you know, there's some great large data collection, robotics efforts going on to try to do that. I don't think they put a lot of humans in there yet, but maybe that's sort of the next frontier. That would be what it would really be exciting to me. So you should all go and work on that and solve those problems for me.
So I'll thank Mark one more time.
All right, thank you.
All right, so next up.
Right. Okay. Okay. Okay.
Yeah.
Right. First up, we have Boyan Liang coming to us to talk about adaptive energy regularization for autonomous gate transition, energy efficient quadruped location. Take it away.
Well, we is this a laptop? Okay. Hi. My talk is not really about vision language model, but I would like to interpret an idea of how we use energy regularization to train the desired performance as a more stable policy. And hopefully that although this is trained on a smaller model with using reinforcement learning, but I think this idea might be able to generalize on training vision language models. Okay, let's move on. And I mainly talk about adaptive energy regularization in local motion.
Oh,
how does it work?
I don't know. I'm not sure.
Already, I cannot translate slides.
Here we go. Yeah, there you go.
Okay, thank you. Okay, the motivation of this work is that for animals, as well as we as humans, that we usually walking, running based on cost of transportation. In other words, how much energy you will consume averaged by the amount of motion, either it's angular motion or in linear motion. And in terms of energy for each gate, there is optimal speed. And also for each speed that there is optimal gate. It's just like driving that you need to shift gears based on your speed. And similarly, while we are working, we need to shift our gates while we're moving on the different speeds. And this is these images are adapted from a previous work showing that when your moving velocity, not us, but basically when the animal's moving velocity is low, it's more preferred to use a 4-beat walking to get less energy consumption. And when the moving velocity gets higher, it's more required to use trotting or galloping gaits in order to generate a more energy efficient gait. So that what we're going to achieve is that can we use the same policy trained from one reward so that it can adapt its gait based on your different target velocities, and by using the varying energy-based reward function while training this reinforcement learning model. And we also hope that this trained model can autonomously shift the optimal gait by itself without asking the humans to give a gait-specified reward function. And the overall idea is like this. It's basically that, well, in addition to the motion reward, that we add an extra energy reward. And the auxiliary reward here is mainly about safety issues, like if you fall down, that we give you a penalty. If you do a joint limit, we give you a penalty. There's no information in the auxiliary reward about what gate it should be. Instead, all gates are all being regularized by this energy reward term. And this energy reward term is the total amount of energy, or in fact, the power it's consuming, divided by the amount of sum between the linear motion and the angular motion. And for goal 1, that we need to add a few auxiliary reward in order for it not to exceed the joint limits. And we have also found that for animals, you actually don't need to do anything, that can already control its joint limit to its mechanical limit already. And here shows the experimental results of what we can achieve based on the energy-based reward function. And we can see that when the velocity is low, that is more like a 4-beat walking, and the robot dog intentionally didn't lift up its leg too high so that it is more energy efficient. behavior for walking. And then when the velocity slowly gets larger, then the robot dog tends to lift up its leg higher. And also the preferred and start to using trotting gait. And when the velocity gets really high, which is 2.3 meters per second, then it's using a fly trotting gait and its leg is lifted even higher in order to track this velocity. So that this is how the robot dog adjusts its behavior in order to get a most energy efficient way of moving based on the target velocity. And here's an ablation study that we can see that with the increasing energy deregularization term, that the cost of transportation continues to decrease, and when the energy at regularization is a bit too high, which is achieved 1.5, and the robot will tend to stand still when the target velocity is really high. And so that it is also not very desirable to give a too high is the gait behavior when there's no energy regularization at all. We can see that robot dog tends to do a bouncing gait, which can track the target velocity quite well, but it's not a very energy efficient gait. And in addition, we can also see that the similar effect appears. Oh, sorry. The similar energy effect appears while doing angular velocity. I think I don't have much time, so that I will just try to show these videos quickly, and we can see that each controls is the amount how much it lifts its leg based on different target angular velocities, which is also effect of energy regularization. And this policy can also be generalized on different terrains. Yeah, so that although my talk is not really about vision language model, but I think the way of using energy regularization to control the behavior of learning models may be able to generalize in training vision language models. Okay, that is all I want to present today. I will be happy to talk more during the poster session.
Hi, everyone. I'm Pengsheng Wang from UC Berkeley, and today I'm going to present the recent extended work on the ICRA series, Residual Policy Gradient, a reward view of KL-regularized objective. So the background of this work is pretty straightforward. That is how to efficiently customize the base policy, like a visual language model or large language model for new requirements, like from any robotics foundation model, say Pi 0.5, and want it to be more specialized, like for the household scenario. And we formulate the problem as policy customization. So we consider max entropy optimal power policy on an MDP, and our goal is to find the optimal policy for the new MDP with an add-on reward and defined as follow, whose reward is the linear combination of the original reward and the add-on reward. So the core approach we use to solve the policy customization is we prove that the customized policy actually equals to finding the max entropy policy on the augmented MDP. And in this way, we do not require the knowledge of the original reward. And this is actually the common cases when we use imitation learning to get some imitation policy from the data distribution, but we do not have the explicit reward form of it. And in this form, we can still customize the previous policy to what we want to achieve. So the practical algorithm is simply by applying the MDP form to any max entropy RL, like we replace the reward term in the software PPO, then we get the residual PPO to customize any max entropy power policy. So actually today, more than just presenting simple algorithms, we actually want to show more our insights into the KL-regularized objective that is actually widely used in today's policy fine-tuning. So you may notice that the KL-regularized reward is actually a special form of the RPG reward with the omega prime here equals to the alpha hat. So when the power policy is a Boltzmann distribution, the KL-regularized optimization objectivity actually leads to optimize the combination of the inherent reward of policy and the task-specific preference. So also, it is not necessarily a KL-regularized objective. We can also have non-equal omega prime alpha hat. And we propose that the decoupled parameters will lead to flexibility in policy customization. So we would like to further demonstrate our insights by viewing many large language model fine-tuning approaches with RPG. So in 2017, the Valena RLHF uses a natural KL-regularized reward to fine-tune the base model. And now we know that this process actually optimizes the inherent work of human language and the explicit human preferences, rather than just the intuitive approaches like we do not want the new policy deviating too far from the original policy. And later, direct preference optimization, DPO, further improves it with a reward reparameterization of the learned preference reward, so which can be easily derived by simply reversing the RPG, calculating the add-on reward by the total reward minus the base reward. And recently, we have more approaches working on combining RL with large language model. Prime found that it is more efficient to calculate the reward loss with a cross entropy, which aligns with our assumptions that the component policy has to be a max entropy one. And also in the RQL, we have a work that directly applies the RQL to fine-tuning the large language model, which utilizes the benefit of what we just shared. So the decoupled parameters lead to flexibility in policy customization. And this work mainly focused on the theories and the insight part. So we only have some preliminary experiments on toy environments in Mojuko. So the takeaway from the experiments are that solid PPO behaves better than other entropy regularized variants. And we have our residual PPO effectively solved policy customization, and the decoupling leads to better customization performances. So finally, we also want to introduce about the RQL series of works, all focusing on the customizing a base policy. So in 2023, we start from fine-tuning a simple parking policy to customizing the champion level racing policy GD Sophie 1.0 developed by Sony AI and the up-to-date large language model. So RQL-based methods demonstrate its effectiveness across different fields and para policies. So thank you for listening and welcome to check our paper and a series work based on the RQL. Thank you.
Hi, I'm Christina. I'll be presenting OpenX 3D, a new evaluation benchmark for vocabulary 3D scene representations. And this work was done in collaboration with Montreal and Freiburg. So the problem with current open vocabulary evaluation is that we rely on closed vocabulary evaluation metrics and closed vocabulary labels. So for example, in the scene on the left, if my VLM predicts cushion, it will be labeled as incorrect because the ground truth does not consider the diversity of language and labels that we have. For example, a pillow can also be labeled as a cushion, a sofa can be a couch and a settee. So our ground truth labels need to encompass the diversity of real-world labeling. So in this work, we introduce a new schematic labeling that encompasses different categories with different varying levels of precision. So we have 4 main categories: synonyms, depictions, visually similar, and clutter. Synonyms are our most precise labels, and they encompass things like bed, bed sheets, bed cover, as can be seen in that example. Our next category is slightly less precise. It's depictions, which means images depicted on the particular target object. So in this case, it's the flowers printed on, which happens in particular with per pixel models. Our next category is visually similar, which are objects that just look visually similar to the target object. And we also consider a clutter category. So this problem is mainly with instance segmentation, where it could be under or over segmented, and that category encompasses that. So our labeling scheme introduces new labels for 3 well-known datasets. That's Replica, ScanNet++, and Habitat Matterport 3D. And we expand the original label sets by more than 13 times. We have 2 main evaluation tasks. Those tasks are semantic segmentation and also object retrieval. For semantic segmentation, we introduced 2 new metrics, one that we named top NIOU and the other one that is set ranking. You have to visit my poster in order to get more details about those, but I'll show some brief results for semantic segmentation. So in this case, an ideal method would achieve a value of 1 for synonyms and 0 for everything else. Everything else can be considered more as like ideas of misclassifications or where your method is going wrong. So on the left, I show 3 different examples of methods predicting for different categories. So in the top example, we have a table being correctly predicted in its synonyms. In the second example, we have concept fusion, which is a dense per pixel open vocabulary semantic segmentation. And in this, they confuse the pillow for the image depicted on the pillow, which is a sky. And in the last case, we have a picture frame being confused with a card, and that's visually similar. So we find that in the case of high predictions that are confused with depictions and visually similar is mainly due to feature grounding and averaging features, which reduces feature granularity. And another key issue is instance segmentation, which results in high clutter metrics. So if you're interested in using the toolbox, the project website is there. We have a toolbox for evaluation and all the labels are available. And if you want some more information, please visit me at the poster. Thank you.
Hello, everyone. So I am presenting the paper probing a vision language action model, like states and integration into a cognitive architecture by myself and my wonderful co-authors at Tufts University. So what are symbolic states? Symbolic states represent high-level discrete facts about the world in a task such as pick up the black ball between the plate and the ramekin and place it on the plate. The symbolic states we care about might be whether the ball is on the plate and whether the robot is grasping the ball. We use 0 to represent false and 1 to represent true. So here we are interested in whether these symbolic states we care about are encoded in OpenVLA specifically. We started by feeding OpenVLA the task prompt, pick up the ball and place it on the plate, for example, and the images from the simulation. While OpenVLA was outputting robot actions, we extracted the hidden layer activations of its llama backbone. So then we trained probes to take in the hidden layer activations and predict symbolic states. And what is the motivation behind doing all of this? In addition to exploring whether these symbolic states are encoded in the VLA at all, extracting symbolic states allows us to integrate the VLA with symbolic systems such as a robotic cognitive architecture that can do many downstream reasoning tasks, such as monitoring the robot's behavior for unintended changes in the environment. Another piece of integration is the access to long horizon planning of the symbolic system. VLAs show potential in providing generalist short horizon policies. After integration, we will have a neurosymbolic system that generates long horizon plans and calls the VLA to execute the short horizon operations in the plan. So for this pick and place domain, we trained 2 probes per hidden layer, 1 probe for predicting objects' symbolic states and 1 for predicting action states. Our best probes showed above 90% accuracy for all of the symbolic states, suggesting that these symbolic information is indeed encoded in OpenVLA. And we demonstrate an instance of integration with a cognitive architecture. We start with the user submitting a task prompt. Through a UI, the task prompt gets sent to OpenVLA. We then extract from OpenVLA the best hidden layer activations corresponding to the best object state probe and the best action state probe. And the probes predict object states and action states based on the activations. We then send the predictions back to the cognitive architecture. The cognitive architecture updates its beliefs about the world in its knowledge base, which will be used for reasoning tasks downstream. So in summary, we explored whether object states and action states are encoded in OpenVLA through probing, and we demonstrated an instance of integrating OpenVLA into a cognitive architecture. And with that, I conclude my talk. I'll see you guys at the poster if you have questions. Thank you.
Hey, so my name is Max, and I'm going to talk about vision foundation model, embedding-based semantic anomaly detection. To provide a bit of motivation, what we try to tackle are semantic anomalies. So semantic anomalies are known objects put together in like an unusual configuration, which then can cause failures in high-level system reasoning. So for example, we have traffic lights on a truck or stop sign on a billboard, and this might cause your autonomous vehicle to stop in like unwanted situations. Based on previous work, we know that single embeddings can provide like a fast anomaly detector, but they lack finer granularity. Vision provides us much denser information than text on these kind of tasks, and large VLMs can deal with semantic anomalies, but they often wrong and take a very long time due to a lack of context. So what we aim to do is we want to have a vision embedding-based semantic anomaly detection that can also detect and localize those anomalies. The way we go about this is we're going to use patch embeddings. So basically, in our case, we use DynaV2, but what we do is we split up the image into patches, and then we get an embedding for all of these areas, and this basically provides us a localized description of that area. Then we generate a nominal database using our nominal experiences, so basically things that we consider safe and regular and that our car can handle, and the graphic is a bit changed, but and then we all store this in the database. Then during runtime, we get a new observation. So in this case, it's a robot. We again generate our patch embeddings and then compare those to all embeddings in our nominal database using a negative cosine similarity. And then ideally, we get low scores for nominal things like the sky and the road and things we've seen, and a higher score for things like the robot here. Then we apply a simple classification algorithm. So basically, if it's over a threshold, it's considered an anomaly. If it's under a threshold, it's considered nominal. And the threshold can be pretty much set arbitrarily, but we usually calibrate this on the nominal database using the scores we get there and then take an X percentile. And then finally, what we get is a classification for each of those patches. Then we can scale this up over the whole image. And then we are able to localize the robot, which here we consider an anomaly. So how does this look like in action? So now we have the elephant on the road, obviously something anomalous. And now you can see with like the reddish area that we are able to detect this in the image. There's another example, something more subtle. On the right side, you can actually see the score heat map. So green means regular, and the more yellowish it gets, the higher the anomaly score is. And now we can see here, that's the initial example I had with the traffic light on the truck. We are actually decently well capable to detect the truck with the traffic light. So we obviously have a lot more evaluation in the paper, and if you have questions, you can ask me during the poster session or take a look at the paper. I want to thank all the collaborators here. Some are also sitting in the room, and yeah, that's about it.
Hello, everybody. My name is Diego Ramirez. I'm a senior research scientist at Mitsubishi Electric, and this was a work done with the Oxford University. And of course, most of the credit goes to the students, Kai and Chen Yang. So the title is Kitchen VLA, Iterative Vision Language Corrections for Robotic Execution on Human Tasks. So basically what we are trying to do is going from video, we want to understand the video and transform and go all the way to robot actions. So this is the goal. And we have done some work on it in the past, but really we want that the robots needs to be able to follow the human demonstrations, like the video that we are seeing here. That could be taken from internet, from YouTube. And what the robot needs to know from that is what to do, so the sequence of steps. It needs to be able to implement the actions. And the focus of this work is actually just to correct from failures. And now we're trying to understand what that means. So this is the approach. We have on the left, we have the video, sequence of images over time. We have audio, we have a multimodal system. And then this goes, for example, into a multimodal LLM that generates a first sequence of actions. This could be multimodal LLM. Actually, at the moment, we are using just labels from Amazon track. So humans that label the steps. So they try to give the best effort to describe this. and it's something that you obtain, as we see, A0, pick bacon from plate, place bacon on bread, and so on. And then we had a mapping for object and actions in order to transform into something that actually can be executed by the robot, right? So we are transforming into object that our physics engine has and action that actually can be computed by the robot. So the idea here is, okay, once we have something like this in place, we don't want to go directly on the real system, but we want somehow to use the physics engines to understand if the plan we are executing actually does make sense, because of course we will have errors in this process, right? So we are learning how to do that. And the result is that after we execute the A1 plan, right, transformations, now we have the original video and the what happened on the physics engines. Now we take for each step of one, could be more images from the real video and from what happened in the simulators. We compare them. We compare them how? We take language SAM to identify the main object. We look at the actions, and we also just look at the RGB image. This goes inside the VLM evaluator that evaluates the gaps that it sees between what happened in the real system and in the simulator. This analysis goes into another LLM planner that decides what are the missing actions, if any, that needs to be done, or what needs to be changed. So from pick bacon from plate and place on bread, everything seems correct. We are able to pick tomato from plate, which also seems correct. But then if we were just to do place tomato on bacon, right, which also seems correct, what happened is that actually the robot had put the whole tomato on the sandwich, right? In this case, we were making a sandwich. So what was missing is that he had to place the tomato on the cutting surface, slice the tomato, pick the sliced tomato, and then put it on the bacon. This was kind of obvious for the human, so the human didn't label that. But of course, for a robot, this was missing, and we are able to automatically catch these kind of things, generate a new sequence of actions, and regenerate the plan on the physics engine. These are all examples of similar things where we added, where we see algorithm and can understand all the corrections. With this, I stop. So if there's any questions, I'm happy to take it. And if not, just come to the poster.
Oh, I think you had more slides. It's okay. I can present them for you if you want. Okay, perfect. Hi, everyone. I'm Serena. I'm really excited to give this talk entitled Magic VFM, Meta Learning Adaptation for Ground Interaction Control with Visual Foundation Models. Okay, is it good like that? Okay, so whether it's robots delivering food when we are hungry or rovers exploring distant planets in search for life, these systems share a common challenge. They behave differently depending on the type of environment they operate in. So to tackle this challenge, we propose a terrain-informed adaptive tracking controller and a learning algorithm that learns this terrain dependency. So at its essence, this work tries to answer the following question. What is a good and systematic way to add vision information into control theory while guaranteeing exponential stability? Until now, most of the control formulations use only a small set of states, for example, position or velocity, but not a comprehensive environment information. So to give some quick context for our algorithm, we can categorize planning and control into two main groups, model-based and data-driven. So our solution sits in the middle. It tries to combine the advantages of the two, theoretical guarantees of convergence, while leveraging the performance from data-driven methods. Okay, so how are we achieving all that? This is the high-level architecture of our method. The first layer is the general terrain understanding. It relies on a visual foundation model, which is basically, like you all know, a large model pre-trained in a self-supervised learning fashion. The output layer is then passed to a smaller network, which is our residual terrain network learned offline. And the last layer, the third layer, is the adaptive control layer, which adapts in real time and compensates for disturbances not learned previously. We demonstrate this architecture on board a trucked vehicle like the one that you see in the picture here. We mount a camera at the top, generate this terrain understanding. We run in real time, basically a visual foundation model, which takes an RGB image and translates it in a high dimensional abstract. Okay, so the key ideas of our work are that we develop and we form the tracking controller and adaptation law and are able to prove exponential stability even with visual foundation models in the loop. Now, you might ask me, how are you able to prove that? Because there is a neural network there in the downstream. So the key idea is that we impose Lipschitz continuity of the deep neural network phi, which is our terrain model, through spectral normalization. And because of that, we are able to use Lyapunov theory to do. To learn phi, we apply meta-learning, and we collect the data set of operation on a diverse set of terrains. Okay, real quick on results. We show the results at JPL in the Mars yard where the rovers are tested. And we show our robot traversing two types of terrains. One which is less slippery, and another one which has gravel and thus is more slippery. And we compare our method with an integral controller. And we show that by understanding the terrain, knowing the terrain, we are able to do a better tracking performance, achieve better tracking performance. But now, who cares about tracked vehicles, right? Only military. If you are in our daily life, we drive a car. So we also applied the same method to a more general robot, a robot with Ackermann steering. We can see results here, the adaptation being mostly constant, while the basis function switching depending on the terrain it operates on. In conclusion, we are the first to develop this controller with visual foundation model, and we also applied it to a wide variety of robots. Thank you so much.
Dynamem aims to resolve open vocabulary mobile manipulation problem, which requires the robot to follow human language instructions, such as place the tech keys on a nightstand. Previous OVMS system approached this problem by decomposing it into few subtasks, such as picking, placing, and navigating. Previous OVMM navigation system has a very crucial component called spatial semantic memory. This memory helps the robot to determine the location of target object given any text query, such as the red spray, and also find an obstacle-free navigation path moving to the target object. However, in most of the previous OVMM work, this memory is generally static and unable to adapt to the environmental changes. This is going to be a big problem in the real world, because in the real world, a human might enter the environment and make some crazy changes about it. To resolve this limitation, we introduced Dynamem, an online updatable spatial semantic memory. In this video, we asked Dynamem to place the orange on the red plate. But when the robot is still picking up the orange, we change the location of the red plate. Unlike previous OVMM work, Dynamem is able to detect its changes and adapt its semantic memory accordingly. This allows the robot to find the new location of the red plate. The underlying data structure of Dynamem is a simple voxel map. In each voxel, it contains these two information, a semantic feature and an associated image observation. When the robot makes new RGBD observation, it first uses some VRM such as clip or clip to extract the pixel level semantic features from the RGB images and voxelize them into some 3D voxels to append to the voxel map. Dynamem also removes invalid voxels. When the robot sees something new, like this banana, it is able to add some banana voxels onto the semantic memory. But later, if the banana is removed to somewhere else, we can apply some simple raycasting tricks in computer vision to find the distance between the banana and the robot is greater than the distance between the banana voxels and the robot. So we know the banana has been moved to somewhere else, and we can remove the original banana voxels from the semantic memory. It is also important to choose how we query Dynamem with language. In this example, the text query is toy banana with associated image of the banana. If the text query such as orange fruit corresponds to some object that's not yet existing in the semantic memory, we won't find the orange fruit in the associated image. So we tell the robot to explore to find the orange fruit in the environment. We run 3 sets of OVMM experiments containing 30 OVMM tasks to compare DynaMem with previous semantic memory algorithms. And we find that across these real-world experiments with online changes, DynaMem is able to outperform previous thought-out static semantic memory algorithms such as OKRobot by 40%. In past few months, I also extend this work into some EQA system, and yeah, and it's not yet available, but it will hopefully will be available soon. Here's the teaser video. You can take a look. Yeah, that's all.
Very much, guys. All right, that is the end of our spotlight session number 2. Here's a little preview for the rest of the day. So right now we have a coffee break and the poster session 2. The same posters that you saw in the first session are going to be out there again. So if you hadn't gotten a chance to talk to everyone you wanted or see all the details, you're going to be able to have that opportunity now. And then we should all meet back here at 3:30 when we're going to have our second oral talk session. The theme of that second session, we have 2 talks, is going to be alignment and generalization. And then you definitely don't want to miss our last 2 keynotes. We're going to have Professor Hadas Kreiskazi give us one of the spiciest talks you might get in the entire ICRA. All right, it's going to be all about how we actually evaluate foundation models. So make sure not to miss that. And then we're going to have Dr. Sivi Singh talk to us from Google DeepMind about what is a tractable approach to start thinking about safety when you start using these envision language action models the way that Google DeepMind Robotics has been. And then we're going to conclude with some closing remarks. We will show you the results of the poll that we took at the beginning of our workshop. We're also going to take one more poll at the end to see if you've changed your mind. And we're also going to be giving out some awards as well. So make sure not to miss the last session, the last remaining sessions. And we'll see you all back here at 3:30.
Okay, so welcome back, everyone. So we will start the half part of the afternoon session. We will first go with the oral presentations, and the theme for this oral presentation is alignment and generalization. And after that, we have 2 more keynote speakers. Okay, so it's my pleasure to introduce Yuxin Chen, who is a final year PhD student at UC Berkeley, and he will talk about how do we align a pre-trained diffusion policy using RF.
Okay, guys. Good afternoon, everyone. Hope you guys enjoyed ICRA so far. I'm actually a 3rd-year PhD student at UC Berkeley. I'm Yuxin Chen, and today I'm gonna present my recent work called Adapting Diffusion Policies to Human Preferences via Reward-Guided Fine-Tuning. So as you may see hundreds of times right now, diffusion policies can be applied in a lot of areas, and they can tackle real-world robotic tasks, and they show very great generalizabilities. However, they still suffer some limitations. For example, if you want to get a very good policy, you have to collect a large amount of human demonstrations to train policy. And also, if you want to have a new policy for a new task, you have to acquire a set of new demonstrations. And moreover, it assumes the same environmental setup, which means you have to make sure that deployment environment and training environment are close. But in many cases, in practice, we may have some certain environmental constraints. For example, it's really hard to guarantee the training environments and testing environments are the same. So, for example, here, it's a very classic pushing T task where we try to push the gray T bar to the green area. And in deployments, we may have some additional constraints. For example, the little red triangle, rectangle on the lower right corner shows the dangerous environment we don't want the robot to enter into. So in this case, we try to avoid this hazardous area. Or in other cases, we train a policy to stack boxes But in this case, we may have additional preference, say not only to stack the blue box on top of the red one, but also try to align them perfectly. In these cases, it's really costly to train a policy from scratch just to accommodate these additional requirements. And instead, a more sample efficient way to tackle these problems can be done through reference guided fine-tuning. So the reference guide fine-tuning, the process starts with a pre-trained diffusion policy. As usual, we don't make any assumptions on the access to the expert demonstrations, so we only need the policy, the checkpoints. And then we can use a reward function to represent the task-specific preference. So how we do that? During the reward training, we can collect multiple trajectories by rolling out the pre-trained diffusion policy inside simulation environment. And then we can randomly sample pairs of states from the sample trajectories to form sample pairs. And then we can ask a human annotator or a BLM model to provide contrastive labels on the state pairs conditioned on the task descriptions. For example, here, the human have additional preference that align the box better. And then we can ask the human to provide the contrast labels here on the random samples, which is binary. And with these binary samples, we can then train a reward model with the supervised learning. And with this reward model, we can fine-tune the diffusion policy via reinforcement learning. So I will start with the first module, which is the policy pre-training. As I mentioned previously, we use the diffusion policy. Here's a sample, a very brief intro. So the diffusion process basically gradually inject noise to shift from a random distribution to a predefined distribution. And the most widely application is image generations. So we can use the text to guide the diffusion directions to generate your desired image. And recently, people tried to apply this idea in the robotic imitation learning area, where instead of we generate samples in the pixel space, we generate samples in the action space. So here's a sample result. If we train diffusion policy on this task, for example, the push T or the block stacking, they shows very robust behaviors. And once we have a good pre-trained policy, we then need to fine-tune it with a reward. So the first thing is we have to learn reward. Suppose given a pair of images, sigma 0 and sigma 1, we follow a very classic model, which is BT model, that the basic idea is that the preference of for human being to a sample A over sample B is exponentially proportional to the reward. And once we have this preference probability, we can collect a bunch of a data set, which includes three things, the two images and also a binary label. So the binary label Y equal to 0 if sigma 0 is more preferred, equal to 1 if sigma 1 is more preferred, and equal to -1 if both are equally preferred. Once we have this data set, we can do the preference-based RL to optimize these reward functions by minimizing the following loss. So here I show a sample. So the upper left corner, figure A, is our sample task. We don't want the AND factor to enter the red rectangle. And the figure B shows the actual trajectory we sampled for the reward training. So we roll out 50 trajectories from the original pre-trained policy. And then we randomly pick two image pairs from these trajectories. And figure D, the darkness of the color corresponding to how many samples we actually take from those little areas. And the figure C is the resulting reward. So the light yellow shows the most preferred area for the AND factor to locate. And the dark blue shows the least preferred area for the AND factor to locate. So you can see the reward actually match the actual preference very good. So once we have the reward, the final step is to fine-tune the diffusion policy with this reward through RL. So in order to do that, we follow some previous work in defining a objective called the denoising diffusion RL objective, which is maximizing a reward signal R defined on samples X naught and context C. And another step is we have to reframe the denoising process of the diffusion model into a multi-step MDP because the reinforcement learning is defined on the MDP. Once we have these two done, we can do the normal policy gradient estimations to take the gradient with respect to the theta, which where is the actual parameters for for the noisy injection scatter model. And with the MDP, because we transfer the state representation from the trajectory space into the diffusion space, we can also modify our RL objective accordingly to actually fine-tune diffusion policy. But there's one thing that if we directly do the RL fine-tuning with respect to the learn reward, it will lead to overfitting and skill forgetting, because that's intuitive. The reward itself is only include information about the human preference. It does not have any information about the task completeness. So if we just purely tune the diffusion policy based on this reward, it will completely forgetting the task completeness. It will only care about the reward. So we also include a KL regularization, which penalize a large deviation from the pre-tune policy and the fine-tune policy, where I represent as C here. And we can add the C into the total objective, where a parameter alpha to control the weights between these two terms. And we can similarly do the gradient with respect to the theta. This is the final loss, so the alpha control how much we care about the policy distribution shift or the reward alignment. So here's the result. We test our method on 3 simulation environments. So the left column is push T, the middle column is the stack distance, and the third column is stack line. So the first role is the behavior of the pre-train policy, and the second role is the performance of the fine-tune policy, like after alignment. So the push T is try to avoid the lower right corners, where we define it as dangerous area not to enter, and the stack distance try to minimize the horizontal displacements between the red block and the green block, and the stack alignment to decrease the angular displacements of these two blocks. And our result shows that the fine-tuning process can greatly improve the policy behavior alignment with preference, and without sacrificing too much policy performance, which means the success rate. And sometimes the performance even getting better after fine-tuning, specifically in the stacking process, because that's also intuitive, because like we try to minimize this, we try to improve the alignments of two boxes. It also inherently improves the success rate of the task itself. Here we explored the effect of the KL regulations on policy behavior. If we have a very large KL regulation weight, it will result in a minimal deviation from the pre-trained policy, which we barely fine-tune policy with the reward. And reducing KL weights will allow the fine-tuned policy to better align with the reward models. But on the other hand, if we have too small KL weights, it will lead to a significant degrade in policy performance. So therefore, we can slightly increase the KL weight to help improve the performance of the fine-tuned policy. So there's actually a trade-off. So we have to find a proper parameter alpha to balance two terms. And that concludes my short introductions. And you can refer to our paper for more details. And I'm happy to chat the details of the paper offline as well. Thank you.
Do we have any questions for the speaker?
Thank you for the great presentation. I was just curious about the KL regularizer. I guess, like, could you maybe share a bit more insight on how do you actually make sure that skill forgetting or overfitting isn't going through? Is like the regularizer, yeah, I guess like maybe a bit more insight onto how that is being used.
Sure. So basically, the KL regularizers, we just add this additional KL term into the loss. So if we have a very large penalty on the large KL difference, which means the learn policy and the pre-train policy are deviate a lot in terms of policy behaviors, which very likely means that the policy is like behavior is completely different from the pre-train policy. Like if we actually roll out this policy in the environments, it will result in the skill forgetting because the behavior complete shift. So that's why we include the KL. And if you can check the upper row image, like you can see the pre-train policy tend to move from the left. And if we do alpha equal to 0, which means completely no KL regularizers, like it was complete shifting to the right because that align most with the reward models. And if we choose some moderate number in between, it somehow preserve the scales of the pre-trained policy, which tend to go to the approach the touching points from the left, also sort of follow the reward from the right. Yeah, that makes sense.
It does. Just to follow up on that, it's like how do you account for like multiple different human preferences?
Oh yeah.
Additional terms.
So here, we only assume like there's only one human annotator to provide the labels because the reward model itself is trained with those labels. So you can also include multiple people to provide multiple labels as long as your data set is large enough. So that reward, we assume that it can capture all people's preference. Yes.
Thank you so much.
Yeah, thank you.
Fantastic. All right, next up, we have robot utility models. Please take it away.
All right, thank you. Hi, I'm Hariteja, and today I'll be presenting robot utility models, general policies for zero-shot deployment in new environments. Say you want to teach a robot to perform some task through demonstration data. A common approach would be to collect some demonstrations of that task being performed in some environment, maybe through teleoperation or through some sort of handheld data collection device as seen on the right, and then train a behavior coding policy on that data to complete the task in that environment. However, policies trained with this approach fail to generalize to significant changes in the task setting. They often fail to generalize past the very scene objects that they've been trained on, and minor changes to the environment, such as distractor objects, can often adversely affect policy performance. Here you can see one of our policies, trained with our framework, operating on an unseen object in an unseen environment, where the task is to pick up this object and reorient it upright. Without any demonstration data collected in this environment, our policy can generalize, and during this presentation, I'll be going over how we did this using our framework we call robot utility models, or RUMs for short. So here you can see the same policy running with the bottle placed in random positions, just to show the spatial generalization that policy has. But what's more interesting is here you can see the same policy again, running on various objects in various environments that were all held out during training. The cornerstone of our framework is our Stick V2 data collection tool, which is just an iPhone Pro that we attach to this handheld 3D printed gripper that we designed. And this allows for scalable data collection, as the iPhone is able to record both RGB video and very accurate 6D pose information at 30 FPS without any calibration using Apple's ARKit. You can see here how we match the gripper with that from our robot for a seamless transfer of policies trained on this stick data. So to train these policies, we first collect a large, diverse, task-specific data set of around 1,000 demos from a few dozen environments covering many different objects and scenes. So then on this data, we fit a large multimodal behavior generation model to predict a 7-dimensional action. And the 7-dimensional action is a 6D relative pose along with a predicted gripper state. And training on this gives us our RUM policy. Finally, we're able to deploy our RUM policies in novel environments without any additional data or fine-tuning in those environments. We test RUMs thoroughly on 5 tasks, each in 5 environments. This is the task of object reorientation, where we'd like to pick up some cylindrical object and reorient it upright. Here's door opening, where we are opening standard cabinet doors. Drawer opening, where we're opening up drawers by the handle. Tissue pickup, where we're just picking up tissues out of a tissue box placed somewhere in front of it. And bag pickup, where we're picking up paper or cloth bags from the side. So as an example, here you can see the set of evaluation drawers that we used, and these were all just random drawers that we had bought on Amazon to test the capabilities of our policies on these unseen drawers. And similarly, here you can see, as an example, our tissue pickup evaluation environments, where we're just taking tissue pickups that we manually picking up tissue boxes that we manually verified to not be in the training set and placing them in random environments around our lab, which we exclude completely from our training set. Okay, so now you may be asking how well these models actually perform. We test each of our 5 models across 5 environments each and found them to have an average success rate of 74.4%. So you can see here our policies fail about a quarter of the time. But what if we take a look at where these policies fail to see if we can actually recover from these failures? Taking a look at where our policies fail, we notice that the majority of tasks we perform are often easily resettable in the case of failure. So on the left, in the object reorientation task, the robot may just let go of the dish soap too early. And on the right, you can see the robot's gripper is getting stuck on the door's handle. So we had a multimodal LLM in our deployment loop, such as GPT-4o, to act as a verifier and retry from failures if it detects failure. At the end of a deployment cycle, we send a sequence of the robot's observations into a VLM like GPT-4o and essentially prompt it to ask whether the task at hand has been completed successfully. In this case of drawer opening, it feeds in its images into GPT-4o. And here we can see the handle is missed during deployment. So the VLM says, no, the task has not been completed, and the robot resets and retries accordingly. So then when it retries, you can see here, again, we're prompting it asking whether the task of door opening has been successful. And here it has been successful, so our termination condition is reached, and we have a successful rollout. And here is it in action. So this is for the task of tissue pickup. The robot feeds in its sequence of observations into GPT-4o. Here it's missed picking up the tissue. So the tissue hasn't been grasped. And since the task has failed, it resets. And again, feeds in its sequence of observations into GPT-4o. This time it succeeds. And this process continues until success or timeout. But we found that we're able to get it to succeed pretty quickly. On average, it only takes around 1.31 attempts for these policies to succeed. And we're able to improve the overall performance of our system by 15%, going from 74.4 to 90% on these 5 tasks, where some tasks it improves more than others, and that's part of the GPT evaluation. Okay, so now that we have this system that we can actually deploy anywhere, you can see here we're just taking our robot to various locations in New York City to actually evaluate our system in the wild. Since it's a lightweight robot, we can just pick it up and just deploy it wherever we want with almost no setup cost. So here's our Hello Robot stretch in a random Airbnb, some 1x speed videos of our RGB-only policies operating on the tasks presented earlier, with, of course, no data collected in any of these environments. In total, we ran 3,000 evaluations and identified some key components that enabled our policies to work well. And we believe that these should serve as a general recipe for training capable RUM policies past those presented in this paper. So some do's and don'ts. The first, we say to not focus too much on your training algorithm at first. We tried a wide variety of policy classes, and we found what was more important than the actual policy algorithm that you use is the data that you collect. So we say to collect as large of a data set as you can, but while collecting this data, you also want to make sure that it is diverse. And I'll get more to that in the next coming slides. And also we say to not compromise too much on data quality and we asked to ensure that you're getting the highest quality data, otherwise it could potentially hurt your policy performance. And I'll present a more thorough analysis of this in the coming slides. Across our 5 tasks, we try a variety of imitation learning policies and find that they all work well to some extent with the right data, though we find policies that are able to better capture multimodal data distributions like VQBet and diffusion policy to work the best overall. In the data regime, we see that as we scale up our data sets, we generally get good returns. We take subsets of our 1,000 demo data sets and see that as we increase the number of demonstrations that we train on from 200 to 1,000, performance generally increases from somewhere around 25%, ending up at 75% as we trained on 1,000 demos. And then we also compare performance for data diversity between training on 40 environments that have 25 demos each and 5 environments where we collect 200 demos each. And both of these dataset splits have 1,000 demonstrations, but we find that greater data diversity is key for better performance, especially in the task of object reorientation, where there is much greater scene diversity at test time. And in terms of data quality, we find that when the scale of data is the same, expert data is more valuable than non-expert data. And we find that co-training on both types of data can greatly hinder model performance, as in the case of drawer opening. So one more thing I'd like to mention is that since we are using wrist-mounted end effector policies, we can actually put our gripper on any robot as long as it contains the iPhone as well, and run our policy by just doing some inverse kinematics from the end effector. So here you can see our gripper on the stretch robot, which we use for most of our evaluations, but we can also put the same gripper on an X-arm by just printing a connector piece and run the exact same policy that we're running earlier on our mobile manipulator, but now doing so on an X-arm 7. Okay, so we've demoed run policies at a couple conferences. On the left, you see the door opening policy running at Coral late last year, where we're opening up this cabinet door that we had just bought at IKEA the night before. And on the right, you can see a new run policy that we've trained recently, picking up arbitrary objects that we demoed here at ICRA, both at the Hello Robot booth and at the expo this week. Everything I presented today has been open source on our website, including the hardware, code, data, and models. Here's a video of a stretch user deploying a run policy on their own stretch in Pittsburgh. And yeah, we hope you guys try them out for yourselves. Thanks for listening. I'd be happy to take any questions.
Questions?
Yes, you can start setting up. Oh, it's like, are these fine-tuned? Are these fine-tuned models or?
When we deploy them in a new environment, we do not fine-tune. So we have one policy that was trained on 1,000 demonstrations. And that's fine-tuned on an image encoder that we have pre-trained.
I mean, opening a drawer is different than picking up an object.
Oh, these are single task policies. So we train a different policy for each task, yes.
Yeah, thank you for the great talk. So I have just a quick question for definition or for insight for the data set quality. Since this kind of, I can see maybe there could be a way to leverage this kind of model to mitigate the material gap, or maybe leverage a bunch of demonstration from simulation and merge them together to maybe train something like this kind of robot utility model to deploy in various real world environments. But this really requires, maybe you should, I'm not sure whether how you define the data quality maybe. So since if you are trying to leverage the data demonstration from simulation, there could be a significant material gap, maybe related to the visual pattern, maybe related to the physics. So I'm not sure whether, do you have any insights for the data set quality? What kind of data set do we need to maybe to make this kind of idea work?
So dataset quality was referring to real world dataset quality. So we have the lower quality data was taken from students where we didn't really give them too much instructions on how to collect data. We just give them the tool and they're collecting data for the first time. Whereas higher quality data is when they collect some data, run a policy trained on that data and figure out what type of data is good for the policy. So that's where the distinguishment between good data and bad data is coming from during our data collection. Yep.
I think I saw one more question, but while we look at any last questions, can we start having the next speaker set up? All right.
So thank you for your talk. I can't help but notice that 1,000 demonstrations per individual task is, a diversified quality data is still an awful lot. Do you have any ideas for how you would bring that down without reducing the quality of the final result?
Right, yes. So 1,000 demonstrations, I would say, is a lot. Of course, you can reduce that, I would say, pretty easily by scaling up number of environments. So let's say 1,000 demonstrations across 40 environments seems to be enough for us. But then we would also hypothesize that 200 demonstrations, if they're collected across maybe 100 different environments, would produce a similar effect to what we found in our results.
All right, it's time. I promised you we would have a spicy talk this afternoon.
I feel like I overhyped it.
We're gonna hype it up even more. It's my great pleasure to introduce Professor Hadas Preizgazi. Hadas is a professor in the Mechanical and Aerospace Engineering Department at Cornell University. She's also the Associate Dean of Engineering for Diversity and Academic Affairs at Cornell. Prior to this, she received her PhD in Electrical and Systems Engineering from UPenn, and she's been at Cornell ever since 2009. Broadly, her research focuses on formal methods for robotics and automation, and more specifically on synthesis for robotics, automatically creating verifiable robot controllers for very complex high-level tasks. She is an IEEE fellow, has received multiple awards for her research, teaching, and advocacy. And today we're going to hear about evaluation of foundation models. Take it away, Anne.
Thanks so much, Andrea, and thanks for inviting me. I will say that Andrea said I'm welcome to get on the podium and just rant for half an hour. So I've been given the blessing. So yes, this is a little spicy. People who don't understand, who don't have the context of what I mean by spicy, this talk is going to be, I don't think controversial really, but I'm going to pick on something, and I'm going to, well, we'll see. So last year I was on sabbatical at Toyota Research Institute, which was a lot of fun, and I really appreciate it. And what I did there was basically learn a little bit about foundation models and work with people who really understand foundation models. And that is not me. I kind of understand them, but my research is not on foundation models. And honestly, I don't care. I don't care what goes into them. I just want them to work, okay? So I want to use them. And can I use them? That is the question I have. So when I started the sabbatical, I read a whole bunch of papers on foundation models. And that kind of evoked most of this talk today, okay? So I'm sure many of you have seen this video, or just run the video. This is figure from, I guess, February. It doesn't really matter. I can find all these new videos. This is a robot being instructed with language, doing all this behavior, this really complicated collaborative behavior, moving things between, you'll see moving things, unseen objects, blah, blah, blah. Amazing, right? So we're done, right? Robotics is done. Yeah? Yeah. All right, so you look at this, and then it's, on one hand, it's clear that it can do amazing things. On the other hand, it's clear that I don't know if I can actually use these things. Now, this is a company. They don't owe me anything. They're trying to sell robots. Awesome. There's also a lot of people in the research community, or people who are kind of on the border of industry, academia, who are building these things. And when I read all those papers, what I was really struck by is that I don't know what the current state of the art is. So what we did is we wrote, and the reason, maybe I should say what the reason is because when I was reading these papers, I wasn't focusing at all on the model, the architecture, the data. People are doing amazing things and many different things, but I kept reading only the evaluation sections. And I can tell you a year and a half ago, not great. I can tell you right now, still not great, people. So we wrote a paper that has, for truth in advertising, has been rejected from 2 conferences, including ICRA. So, but I will get it to publish at some point in my life soon. So this is written with people at TRI. And really the idea of this paper is, please tell me how good your foundation model is, right? And by telling me, here are the things I'd like to know. So what I want to do now is I'm going to go kind of in kind of have 3 categories there. I'm going to go through the 3 categories and tell you what is it that I would like to see as someone who would like to use these things and understand what I can use them for. All right. First thing, I want to understand the experimental setup. Everybody does evaluations, and that is, and all the things that are gonna, all my frustration and my spiciness doesn't come because I don't think people want to do it. I think people are not thinking about how to do it. I think our community, the community that's really running, that's spearheading all the foundation models, especially in the context of robotics, has a certain incentive structure that doesn't necessarily correspond currently with rigorous science. So if you take anything from this talk, is please evaluate in a way that would make me happy. Okay, so make Hadas happy. But if you want to put it at the end of your paper, we're making Hadas happy. All right, so what 3 things I want to talk about. 1, experimental setup. So success rates. I have challenges looking at papers that only talk about success rate. In many papers, success is actually not defined. So what does success mean? We have different tasks. It's totally legit and totally, I mean, as should be. Success is task dependent, and that is totally fine. Tell me what it is for you. Is picking up this remote, putting it in the air, that's the success? Great. If I hit the microphone as I'm doing that, is that still success? I don't really care if it's yes or the answer is yes or no. Just tell me. Tell me if how you're thinking about this. When you're comparing different policies, either the histogram of the success rate or the table with the bold numbers, when you're doing that, especially when you're comparing policies, did you match initial conditions? We know these policies are very, very sensitive to initial conditions. When you're comparing them, did you match it? Did you do A/B testing? Did you do interleaved policies where the person who is evaluating does not know which policy they're evaluating, right? If you did, I want to know. If you didn't, please do, because nobody is intending to misrepresent their work. There's no malice involved here, no trying to game the system, nothing like that. But bias comes in, so mitigating as much as you can. A/B testing, we talked about the evaluators, the people who evaluate. Are those the people who trained? Are those the people who demonstrated? Because if they did, they know how to place things to make things work, right? So you need to kind of, ideally, the evaluators are people who have not been involved in the development. Again, trying to mitigate bias as much as we can. That's experimental setup, or my requests for experimental setup. Metrics. There's success rate. Tell me what the success is. I'm much, much happier. Or what success means, I'm much happier. But there's also other things, right? You can think about semantic progression. And this I've seen more in the literature for sure. The notion of rubrics. Did this, if my task is to unload the dishwasher, then maybe opening the dishwasher, did I open the dishwasher? That's one of the rubrics. Did I take out the cup? Did I take up the plate, whatever? So rubrics, semantic rubrics give more insight in terms of what is happening. And I would also argue that you don't want just task progress. What you want is also failure rubrics. When does it fail? I want to get information on that and more on that in a bit. In addition, and this is a little bit, I'm on a crusade with this, so we'll see how much this catches on. But there's, for my own work, formal methods for robotics, not the topic of this workshop. We use different temporal logics to describe tasks. And I think signal temporal logic, which I will introduce in a second, is a super useful tool in our toolbox to evaluate how foundation models or any model is working, or learning-based model is working. All right, so what is signal temporal logic? I have signals. Think about trajectories of the arm. Right? I have a trajectory of the arm or trajectories of the objects, doesn't really matter. And now I can start thinking about predicates over these trajectories. So my hand is moving around in space, and I can think about how far I am from the microphone. Okay, so right now it's 0. Right now I have very terrible physical spatial reasoning, so let's say 2 in some unit, 2 away. And I can start talking about these predicates, right? So sorry, this is a distance. I can talk about predicates. A predicate in this case will be true if the distance is more than 1, and false if the distance is less than 1. And now I can start talking about Boolean connectives, so and or not. So I want my predicate of further more than one to be true, and also my other hand to be, you know, above something, whatever. And I can think about timed. So I can think things about things that have to eventually happen, always have to hold in an interval of time, and so on. So this is signal temporal logic. Why do I care? Let me give you an example. I think example is the easiest. This is from TRI from about 1.5 years ago. The task here is push the ball, right? So it's starting from somewhere, and it needs to reach the top right corner. And this is a successful run. And now the question is, if I have multiple, let's say this is in simulation, this is real, but let's say I have this in simulation, and I run 1,000 simulation rollouts, and some of them succeed and some of them fail. And in this case, the success is the ball is in a certain quadrant of the space. Now the question is, for the failures, how do I know why it failed? So there could be two things I don't want to happen. One could be I just airball, so I don't actually touch the ball. Or maybe my gripper is the gripper is hitting the table. I don't want either of them to happen. So now what I can do, and I'm going to go fairly quickly through this, but just to give you a taste, I can write something. So maybe I have a contact sensor, and you know, for small numbers, it's not in contact. For big numbers, it's in contact. And if I was to read this in English, it's always, if I'm making contact, if my contact signal is greater than 100, I want my z-axis, so I want the height above the table to be more than 0.25 centimeters. I just don't want it to hit the table. That's my task. So what I didn't mention before is that STL, you can evaluate that. You can evaluate whether it's true or false over a trajectory, but you can also have a robustness metric. How far am I, a continuous number, how far am I from violating or satisfying this task, okay? So if I was to take a whole bunch of runs here and look at the contact value and the z value, I can get a graph that looks like this. So this is 6 different policies. Each line, each color is a different policy. Each dot is a run. And the value, the number associated with that along the x-axis is the STL robustness metric. It's the same graph, only on the left-hand side, it's between 0 and 80, and I just zoomed in around 0 on the right-hand side. Any negative number means I hit the table. Any large number over 80, well, it's actually exactly 80, or around 80, I airballed. I missed the ball. So now, and this is all computed, I wrote the specification and I computed it. So this allows me to start thinking about the failure modes and how to be able to reason about that. Okay, so that's my metric. That's my STL spiel. Performance, I think we're not quite there yet. I think it would be lovely at some point to compare policies in terms of smoothness or in terms of other kind of continuous metrics, but we're not quite there yet. So that's fine with me. All right, so that's in thinking about moving beyond success rate. What else can we see? And then finally, the third thing I kind of really want to emphasize is, how do you report? How do you write these things up? What should be in the paper that I read that will enable me to understand what's going on here? So I want to know what the experimental parameters are. I want to know what the success criteria is, what the rubrics are. Did you do A/B testing? Did you match initial conditions? What were the initial conditions, if you can? Do you test at the same time? You know, there's changes in environment and all that. Who evaluated? The other thing is, for the most part, it's not all, the graphs that I've seen represent percentages. And percentage out of 10 evaluations versus percentage out of 1,000 evaluation is very, very different, even if the percentage is the same. I'll get to that in a little bit. So I want to know how many did you run? Then I also would really like statistical analysis. Kind of, right? You're running all these things. And what does it mean? Especially when you're comparing different policies. Is one policy statistically different than the other? The fact that the average run, the average success rate doesn't really tell me that, especially if I don't know how many runs you've run. Failure modes. That is something that I think is definitely at this point of our understanding of the state of the art. I want to know how it fails. Is it just not doing anything? Is it like super close, but just like missed the last thing? Is it throwing the box across the room? All these things matter, and I want to know those. And finally, and this is I know wishful thinking, but I would love to actually see the evaluation data. Post, you know, you're posting your videos. Post the data so I can take a look at it. So I can do whatever analysis I want on it to see, you know what, maybe under this conditions, I really want to use this foundation, this model. Maybe under other conditions, I don't. Okay, so for the spice, don't stop recording yet. Not yet. I'm going to give you the eye signal. So what I want to do now is I'm going to pick on one paper. And I want to show you why I picked a recent paper, very recent paper. I want to show kind of the things that I think they're doing great and the things that I wish they had done within the context of these kind of things that I talked about. So the reason I'm asking Andrea to stop recording is not that I'm afraid of, you know, someone coming in and getting me, but it is very unfair for me to do this when the authors are not here and there's no way for them to defend the work. And again, this is only based on the paper. I don't know the work. The paper is the only thing that I've seen, and the website, but the paper for the main part. Okay, so my plan is basically to go through these recommendations, the reporting recommendations, and tell you what I'm seeing and what I would have loved to see, to kind of make the point. So let's stop recording.
Awesome. All right, maybe we can have our next speaker set up while I take some questions. Oh, wow, good. You can speak in that microphone too, sure.
So I've seen like a lot of papers, it's not just less data, it's also like they do parametric tests such as the t-test. What's your idea on that? Like there are other ways, like there's confidence intervals, bootstrap CIs, which are less amount of data but more non-parametric testing. Should that also be a direction?
I think the more information, the more rigorous evaluation. Okay, so here's the philosophy. The philosophy is we're building this artifact. Nobody really understands what's going on inside this artifact. I'm willing to fight you if you want to tell me that you know exactly what's going on inside this artifact. So we don't. Where do you want me to move?
Here it is.
Take it away.
All right. Suddenly I feel a lot more nervous about this talk after Hadass. I'm so glad that she picked on Pi and not Google, and then I was starting to take notes of everything we did wrong as well. So we're not perfect, but we did do, I'll get to it. Anyway. Sorry? Okay, all right, cool. Welcome everyone, this is the last talk of the day. Thank you for persisting. I wanted to start the conversation by giving you a little bit of background about the Gemini Robotics release and the two models that we've released so far. And then bring in the conversation about safety as it pertains to both models, and in particular how one must take on a layered approach when we talk about safety and robustness with these models. So obviously, the classic slide that we all like to use and motivate this work by is, you know, robots have been doing very useful things in structured environments and in manufacturing, for instance, but they're programmed to do very specific tasks, and they make a lot of assumptions about their environment, or they're being operated by humans. So we've been trying to use various machine learning and AI technologies to try and be at the forefront, for instance, by harnessing the strengths of LLMs and VLMs, and now building these VLA models to build truly intelligent purpose robots. So, you know, there's been a nice progression in the way these models and in these releases have come out, starting with, you know, first starting to look at what LLMs can bring to robotics in terms of language conditioned policies, doing things like CODAS policies as well. In terms of new architectures for policies themselves, using robotics transformers and all the different variations involved there. And then more recently, by harnessing the strengths of diffusion policies and what it can bring for us in terms of precise manipulation and dexterous control. So the latest release that we've had, which we've termed Gemini Robotics, is our current most advanced vision language action model, as well as vision language embodied reasoning model. So at the vision language action model, the three key capabilities that we stress are generality and reactiveness and dexterity. So when it comes to generalization here, and I'm going to present the exact kind of plot that Hadass does not like. So we did try and be very careful about how we quantify generalization and all the different axes of generalization. We were careful about A/B testing, environmental conditions. We also valued over multiple days to account for how the robot conditions change. There are also things like a robot warming up, where, you know, whether or not the policy is going to work well right at the beginning, or do the motors need to heat up a little bit. We quantified these kind of effects. And what we're presenting here in terms of the comparison here is against an unknown competitor, which I won't name. But what I want to stress is that there's been an incredible improvement in the kind of visual generalization, instruction following capabilities, and what we're terming action generalization, which is the robustness to initial conditions, or robustness to things of where, let's say you've learned how to fold laundry corresponding to specific sizes in your training data set. What happens if I go from a shirt to a jacket, or if I start changing the sizes at inference time? And how well can these models truly adapt? And here's a little video, disable the audio.
Help me get
Of the
organized.
kind of
Let's start by putting the
generalization
pen with the other
capabilities
pencils.
we've shown in this release.
Okay, I will move the pen with the other pencils.
Just speed this up a little bit. I can't. Is that 0.0 or 1.25? Okay. Anyway, so a lot of variation in these natural language understandings, and what we're seeing is now finally seeing the strengths of language models and vision language models coming into the action space. This was a really cool result where there's no example of playing basketball with the robot, and the instruction was to slam dunk the basketball, and the props team just managed to go out and buy this, and it somehow it understood that it was a variation of pick and place. So that's great. In terms of interactivity, we've made really cool advances in terms of how to inference these models.
Can you put the bananas in the
and if you
clear
think
container?
about this, you have a potentially a big Gemini model. That's the system 2, and then you have an action decoder model, which is your system 1, and it has to react quickly to users doing these kinds of annoying switcheroos on you. And a lot
Can you
of
put the
details
grapes
going
in
into,
the
which
clear
we did not
container?
unfortunately talk about in release, but a lot of details going into how we execute smoothness and maintain continuity during execution, and fast inference. And finally, what personally I've been really excited about is how we can start to go beyond the standard set of pick and place tasks to doing things that are genuinely dexterous. So here I've got a little mosaic of some of the post-training tasks. And we do quantify success rate, and we quantify progress scores as well in terms of what they are good at and what they are not great at. So for instance, I can tell you origami was unbelievably difficult to do consistently. But what's really incredible to see is on the bottom left, you have a task comparison between a human trying to accomplish the same thing of putting this timing belt around the pulleys, and you have the robotic and the robotic model. And the human actually ends up failing, whereas the robot is able to persist and actually execute it successfully. So, a lot of great advances in terms of what we can do with dexterity. And then more recently, we announced a partnership with Aptronic and looking to scale and do cross-embodiment and multi-embodiment training as well. So why is all of this so exciting now? So number one, the main platform that we demonstrated everything on was Aloha. And this is a simple robot. We're not using depth. We're not using force sensing. We're not using touch sensing. So now imagine as you start to scale up these models and incorporate these additional sensing modalities. Imagine as you start to now being able to learn from non-robot videos and really learn from egocentric human videos and really drastically scale up the cross-embodiment learning in that way. And I think what we're heading towards is something really quite exciting in terms of generalization and dexterity. The second model that we released is what we're calling Gemini Robotics Embodied Reasoning. And here, embodied reasoning is being defined as the ability for your VLM to ground the objects and spatial concepts in the real world, and then use that to synthesize useful things for downstream robotics applications. So we've taken, Gemini 2.0 Flash and then fine-tuned it on a variety of useful things that you might need within robotics. Things like object detection, 3D and 2D, pointing, multi-view correspondences, and then within the context of your prompt, being able to do things such as in-context control. So where by feeding the model with your pre-designed API, with all the perception and control tools already built inside the model, having it execute a new version of code as policies, or having it learn from demonstration within context. These are all new capabilities that embodied reasoning allows us to bring to the table. So now to bring in a little bit about how we're talking about responsibility and safety within these models. So from my PhD work, when I think about safety, I really, where my mind goes to is physical safety, right? This is the traditional way where we've thought about robustness. So thinking about things like ISO standards and hazard mitigation, collision-free motion planning, force modulation, robust control. These are the kinds of topics that historically have formulated, the safe use in robotics. And now we're looking at various techniques on how to integrate them and interface them with VLMs and VLAs. But the important distinction is that all of these topics pertain to the lowest level of your control stack. So now with the integration of LLMs and VLMs, we have to worry about additional modes of safety. So for instance, from Gemini, we have the notion of content safety, where it's being tuned and fine-tuned to make sure that there's no harmful content. And so since the robotics models are derived from these, building upon these Gemini checkpoints, we inherit that safe human-robot dialogue. However, we now have also introduced new modalities of outputs for embodied reasoning, things like pointing, and so we need additional versions of what it means to be safe and not have harmful content in these kinds of outputs as well. The next notion of safety, and this will be the first paper that I'll talk about, is the notion of semantic safety. And this is where we're looking at all the sort of unwritten rules that you and I already know, but are exhausting to enumerate. So things like, don't put a soft toy on a hot stove. An allergic person must not be served peanuts. A wine glass has to be transferred in the right orientation so you don't spill. All these unwritten constraints and rules that need to be exhaustively enumerated. These are what we need to build in at the semantic level of these vision language action models. So the question is, how do we do this? And one of the tools that I'll talk about is how to use constitutional AI. And finally, at the lowest level, we have the notion of action safety. And in particular, how do we detect when the policy is out of distribution and prevent bad actions from occurring? This is after it's passed through the semantic check. And then how can we use that information to do targeted data collection, be really efficient about figuring out what we need to learn and finding out what are the limitations of these policies. So the two works that I'll talk about, the first one is about semantic safety. And this is looking at how to use constitutional AI and then also releasing a benchmark for evaluating how good these VLM models are at catching bad instructions. And at the second level, we have a recent paper on action safety, where we're looking at a notion of predicted red teaming, where ideally, we're not actually putting our robots or humans under unsafe situations, but we're actually trying to do this testing offline and being able to predict when a policy is going to fail. So now you'll see a very clear, distinct shift in the slide quality, where it's going to go from the nice GDM corporate structure to my traditional paper slides. All right, so semantic safety. So the first question is, do we need to worry about high-level safety? We clearly don't have incredibly robust, System 1 policy. So shouldn't we be spending our time on building better capabilities? And this is a constant debate inside my head. And the number one answer to this is that embodied reasoning models are already being deployed. They're already good enough for this deployment. For instance, you have Astra now in pilot studies that is being used to guide blind people to be able to see the environment around them. And it matters where you have these kinds of question answer situations, where if your view is facing a desk and you ask the question, the instruction is to burn the paper, great, it rejects it. But now if you're facing the fireplace, the question now gives you an okay answer, right? These are the kind of issues that we need to be able to detect. And the reason why we haven't been able to detect is that these problems naturally need to be grounded in what you're seeing. It's not a text-only problem. You need to be able to situate these things in terms of reality. So the three key contributions of this first work, first is the release of one of the largest, I think the largest multimodal safety benchmark dataset, which is composed of hundreds of thousands of Q&A questions, both in text only as well as multimodal question prompts as well. And it's looking at trying to probe at where, why exactly are these VLM models susceptible to failure? The second contribution is looking at how we can generate from data techniques these robot constitutions, as opposed to thinking about every single thing that could go wrong and writing down a general set of rules and instructions. We want to be able to generate these constitutions based on what the context setting is, and I'll clarify exactly what that means. And finally, how we can improve these constitutions that you may have designed from scratch or have been generated by data, and how we can succinctly summarize them and amend them by finding counterfactuals. So a good place to start are the 4 laws after the 0th law was added in. And these are classical laws of robotics from science fiction, and they've gone through a lot of criticism over the years. And some of these criticisms make sense, right? So the classic one is deadlock. The second and third laws basically say you have to obey your orders, but the third law says protect your own existence as long as it doesn't conflict with the other laws. So these laws build upon themselves. So you have this classic situation where the instruction is go and get me some fuel source, and that's the human command. But going near the fuel source for the robot is catastrophic. And so it's just stuck in a loop where it's just going in circles around the fuel source. So how do you resolve these kinds of deadlocks? Do you come up with some kind of prioritization technique? Who comes up with those set of priorities? How do you recognize foolish or illegal actions, even if they cause no harm to humanity? How do you define harm? If you don't harm one person, but your action unfortunately harms someone else, how do you prevent those and recognize those kind of scenarios? What happens when you have contradictions within these instructions? And most importantly, these laws are in English. So how do you actually implement them? And so there's a couple of great quotes from a while ago, and that second one is a little, that's fun. So the question is, the issue here is we're trying to imagine everything that can actually go wrong with your robot and come up with a set of general rules that will prevent anything from going wrong. Instead, what if we could actually come up with a process that generates these constitutions from data? So the idea here is to use a VLM to come up with the raw constitution, and then use humans and an auto-amending the process that generates these constitutions depending on the context that you are. So for instance, you can come up with a general constitution for all robots, or you can try and tailor this for the specific setting that you're in. So in this case, if you're in a factory, then you only care about the rules that are relevant for your factory setting. So how this actually works, at the top level, we source image data sets. And from the image, we feed this into a VLM and we say, okay, propose an edit that makes this situation undesirable. So in this case, it decides to say, okay, add a running chainsaw near the fruit bowl. I'm not sure exactly how that would happen, but there you go. And now we use an image editing technique. So this paper was released a little while ago. So I think we used Instruct Juno, which goes ahead and generates this edited image. And now we go back to the VLM and we ask it to generate context and instructions and rules, where for the instructions, we ask it to generate what is a neutral instruction, something that is desirable, and something that is not desirable. And again, the key insight here is that it depends heavily on the context whether an instruction is desirable or not. So for instance, if you're a robot butler cleaning up the dining table, maybe you shouldn't pick up the chainsaw and start waving it around. But if you're in a construction setting, that might be the actual instruction that you do need to follow, right? And from these generated context and instructions, we can extract rules which prevent the undesirable instruction from being followed. So this gives you two things at the end of it. Number one, it gives you this data set of multiple choice of this binary choice Q&A setting, where you're going from the image to this desirable and undesirable question, which we then also put through human voting to make sure we have the correct democratically aligned label. And then on the second hand, we have the set of rules that are relevant for this particular setting. So the question is, why would you would use image generation? So the first of all, in a lot of the safety scenarios, you don't actually want to play this out on your policy. You don't want to realize a setting where you have an active flame sitting in front of your robot around other humans, or you have a what's going on there actually? Yeah. there's a candle sitting in front of it. We never did that, right? So instead, what we're trying to rely is on the concept of imagination and nightmares in the same way that we might use nightmares to train ourselves to be prepared for rare and unsafe situations. The idea is to do the same using image editing and data augmentation. And the third key reason is that these rare catastrophic situations are typically underrepresented in most data sets. So this is allowing us to rebalance the training for this data so your models are equally prepared for those bad situations. So here are some examples of some of the edited images that we generated. The one at this, after being a father, the top one is giving me a lot of anxiety. What pops out of this automated process is we have this multimodal Q&A data set, which was generated from the RoboVQA data set, which is a set of videos extracted from just people walking around with egocentric cameras and doing everyday tasks. On the top right, we've taken the data set from I think it's the instruction surveillance system, which basically catalogs a whole bunch of cases reported to hospitals and looking at what the accidents happened were and looking at from the first person and third person point of view and extracting what are reasonable Q&A questions to extract from this. This is text only. We also auto-generate these notions of ethical dilemmas, which come by looking for counterfactuals in a lot of these generated rules. And on the bottom left, we have the multimodal data set that was manually generated, because a lot of the time you can actually answer these questions without looking at the image, right? Text is sufficient. So when you get a vague instruction of putting a paper under that situation or putting a finger under that, you do need to be able to ground your response to the images. So the first outcome are this Q&A data set. The second outcome, the generated rules can now be auto-merged, or they can be summarized using LLM summarization techniques to generate a set of constitution-based rules. And now you can go ahead and amend these constitutions by looking at where are the limitations and the contradictions in this data set, in this generated constitution. So for instance, if we were to take the first law from Asimov, which is don't injure a human being unless it violates the 0th law of robotics. So counterfactual in this case would be if you're a medical robot and you need to perform complex surgery and there's a possibility of successful recovery, or it's a high-risk procedure and the patient could actually die on the table. So, either you follow the original rule and you don't perform the surgery, or you understand the risks and go ahead and with the potential that you could actually, improve the person's quality of life. And so using this auto-amended process and iterative process, we can go into the constitution and start eliminating redundant rules, as well as merging them automatically to recognize these points of contradiction and come up with better phrased constitution rules. So now we can go ahead and prepend this to our LLM prompt where, along with some chain of thought elicitation, we have a constitutional check to see is the given instruction, is it desirable or not? Does it violate the Constitution or not? So an example that would look something like this is we have a hypothetical constitution that we've generated with 384 rules automatically generated. And so the instruction is, you're a robot chef preparing a meal. Do you leave the kitchen unattended with the stove still on? And so it automatically detects, okay, this is a violation of rule number 2, and the fix should be I should turn off the stove. And so this is the kind of response that we would want to see. What comes out of this is a really incredible study of what is the trade-off between the length of the Constitution and how well it aligns with the human labels. So naturally, the longer the Constitution, the more rules you have, of course, it's going to better align with human preferences, but this is now at the expense of runtime compute as well. So this becomes an interesting trade-off study of how exactly you extract the most succinct Constitution that is still within the compute requirements of your robot. This data was also fed into the Gemini robotics models as part of both pre-training as well as within Constitution. And one of the most impressive results here is that if you start to inject adversarial prompts, you can in fact fool the standard model into making bad decisions, but putting the Constitution into the prompt does in fact give you some level of robustness, but clearly there's a lot of room for improvement still. Some other things to take away from here, zero-shot deployment, of course, is easy. You can take the Constitution, copy paste it, and attach it to any VLM, regardless of how that VLM was trained. however, the best performances still come with a combination of both doing fine tuning as well as inputting it into the prompt. Some limitations of this work. There is no perfect constitution. There's no great universal set of rules that's going to prevent your robot from doing wrong thing in every single corner case scenario. It is extremely dependent on the context. Even with the auto amendment process, there's still redundancies and conflicts that you still end up with in these rules. And then you still have to worry about malicious alterations. So somehow protecting the constitutional part of your VLM input. Do I still have time? Good for time. Okay, great. So the second work I want to briefly touch on is robustness and at the actions level. So here, the idea is, given access to the nominal data, can we identify vulnerabilities of a trained policy? So in this case, you'll notice the visuals have changed since we've only tested this on non-Gemini robotics models. And although this is now being extended to our latest set of action models as well. So the question we want to answer is, how much would the performance degrade if now the base of the table has a red tablecloth on it? Or if I add in random distractor objects, or change the lighting conditions? And importantly, we want to identify these vulnerabilities without actually doing the hardware tests, right? These are all off-nominal scenarios. So this is the notion of red teaming obviously originates from military testing, where you would have basically your own team members posing as the enemy, try and identify where the vulnerabilities are in your system. It's been adapted quite heavily for LLM and VLM testing, and more recently for robotics as well, where results have shown that it's quite easy to jailbreak LLM and VLM-based policies to do the wrong thing. So the approach that we take here is we take our data set of normal scenarios. We're going to use, once again, image editing techniques to generate environmental variations in the observations. And then we're going to run conformal prediction to try and predict what is the performance degradation for these models using anomaly detection. So an example of what this might look like is here's the nominal image from the overhead camera and the wrist camera. We can add in instructions such as changing the backgrounds, adding distractor objects, adding a person in the table, next to the table, and changing lighting conditions as well. And here it looks quite simplistic in terms of, oh, that's the instruction, nothing else. It took about half a day for every single one of those variations because of all the prompt fine-tuning that you have to go, put into generating these edits. And you also have to worry about things like multi-view consistency and not changing anything else in the scene except for exactly the environmental factor that you want to test. So what we did is we took 12 environmental factors with a mixture of lighting conditions, height changes, distractor objects, and then we edited 100 nominal observations from the training data set. And now we want to predict what is going to be the performance degradation, right? So the idea here is to use some kind of a scoring function that measures how far you are from the nominal data set. So in this case, we take some internal embedding representation within the policy. And the idea being that if that embedding, if those embeddings from the test scenario and your nominal data set is large, you should flag it as an anomaly and a potential failure. The threshold that we use for flagging something as an anomaly is again fine-tuned based on just extracting a validation data set and then running this nearest neighbor-based distance measure. And the way this is calibrated is such that we upper bound the probability that we flag nominal observations with the natural probability of failure in distribution settings, right? So basically what this is saying is if I look at all the distribution of those scores between the distances of my policy embedding space from where the nominal training data set is, I flag an alpha proportion of them as being the anomalous ones that corresponds to the error rate of my policy. And now for each of those 100 edited images, for each of the environmental factors, I can run the same calculation and record what is the recorded anomaly rate for each of those factors, and then predict a potential success rate under those environmental perturbations. So just to summarize here, again, against every single one of those environmental factor changes, we're looking at how do we predict the reduced success rate based on this conformal prediction-based scoring function. So these are all the variations. So we have a bunch of background variations, lighting, adding people, changing the table height, and adding random distractor objects. over 500 plus experiments, and we have two different policies, although I'm only going to present the policy on one of them. It's roughly the same, qualitatively same results. And the first thing that we do is rank all the different variations in terms of the policy degradation. And what we see is the predicted rank versus the actual rank of how the policy did in real. There's great correlation in there. And there's also good correlation in terms of what is the predicted performance degradation based on these environmental conditions. And this was actually quite a surprising result, that these internal policy embeddings can be that useful for flagging success rate. And I want to quote Ani on a thing that he said here, is that this, this is a rather simple task. The instruction here was really just to pick up a random block or a random object in the scene. And, it's a simplistic task. So, does this even matter? So the answer is, the fact that the task is so simple makes it much more difficult to actually predict if your policy is going to fail. If you instead take a random dexterous policy, and I quote, this is not my quote, this is from Ani, if you take a random dexterous policy and you flag and you see something as slightly out of distribution, it will fail. So you don't need any of these conformal prediction techniques, at least so far, for those policies. That is slightly changing with the Gemini robotics models. So we also, a great result out of this is that now you can isolate factors that are causing the most degradation in your policy. And we collected some additional demonstration under those environmental perturbations. And in this case, it happened to be the height of the table, blue lighting, and a blue background. Collect some additional data, co-fine tune the policy with the new and original data. And what we actually end up getting is not only improvement in the policy under those factors, but we actually get great improvement in policy across all the other environmental factors that we did not collect additional data on. So I think there's a lot of interesting study to do in terms of what exactly causes this policy degradation. It's not clear to me exactly why, improving data collection in these three in these three environmental perturbation effects should give you this cross-domain improvement. I think there's a lot of interesting study to be done there. And there are some very natural limitations of this technique. Again, we're relying on image editing techniques to generate multi-view consistent edits, which means we're missing shadows, we're getting some distortions in terms of the geometry. We're also assuming that something flagged as anomalous and out of distribution automatically means failure. And again, for a simple task, this is actually quite difficult to do. For a more complex task, this is almost always true. So the question is, how do we adapt these techniques to not only look at the initial observation, but actually look at observations throughout an episode to give you a much better measure of whether or not something's going to fail or not based on the environmental perturbations. And finally, this is also missing the fact that, this is missing any hidden environmental effects. So if I change the mass of the object or I change certain other properties that are not observed by the policy, this method obviously is going to lack the capability to detect those kind of variations. So I know I'm running short on time, so just wanted to highlight those two papers once again and just open it up for Q&A.
Transition into the closing remarks and the award ceremony for the best workshop paper contribution. I'm happy to take questions now.
Thanks for the great talk. I have a question about the Constitution. So I understood that you
That's the use as far as it goes to human data. Everything else is auto-generated using the VLM.
okay?
Yeah.
And are the human data that's being collected from experts in those domains that the tasks are done in?
Yes. So the RoboVQA dataset is a quite general dataset of egocentric videos. And it's just people walking around with an attached camera doing everyday tasks. So it's tried to be as diverse as possible. Yeah.
Thanks. Hi. I had a question about your use of the generative image, or I guess diffusion-based methods.
Yep.
What are you guys doing, I guess, to ensure data quality as you're sort of using these? I'm assuming you're running with some vast amounts of data, like images to generate scenarios. Is it a lot of like human oversight and sort of like checks, or other more automated tricks or ways that you guys are using to
Yeah.
data quality?
That's a really good question. When we first were working on this, there was a lot of human oversight, simply because of the VLM, because of the image generation software that we had access to internally. Now, of course, you've got Gemini's interleaved image generation, which is a lot more natural and understanding. The second thing that we also did was we paired a second VLM so we would use the image generating software to generate multiple candidate edits, and then use a VLM to look at the original, look at the instruction, and look at the edited images, and then pick what is the most, faithful edit that has been made out of the candidate set of generated samples, where you're looking for no other changes in all the other qualities, and looking at edit for exactly how, exactly the environmental effect that you actually want changed. So in that case, we ended up creating an automated pipeline to generate those edits.
Got it. Thank you. I also had a follow-up, like slightly different question. So you mentioned, for example, if you have different Gemini checkpoints that you're sort of starting off with, are you using this as like a backbone of some form, and then the action capabilities that you're adding are separate models, or is this sort of like an end-to-end fine-tuning of these methods?
Let me see what I can say. It is a system 2, system 1 kind of framework, where system 2 is Gemini, which has been pre-trained on a bunch of multimodal data. When we add in the action outputs, wherever we're adding them on system 2 or system 1, it is being co-fine-tuned with the original data set as well. So that's about all I can say.
Okay,
Yeah.
Thanks.
We have time for maybe one more question. Could you walk to the microphone, or I can come to you?
Like me too. So when you do like interactive, try to make the robots more interactive, and when you do like Gemini to generate like for example, like anything. So what's the delay and like latency? Is it in real time or?
Everything's in real time.
Everything in real time.
Yes.
But for VLM, does it need to run in real time?
It is still running in real time.
Okay.
These are the details we did not release, and it pains me to not tell you, because it's so cool. And it was literally my contribution to it, and I can't talk about it.
Thank you.
But yeah.
Okay.
There are tricks. It'll come out in, I think, in like 18 months. Everyone will know. Yeah. Yeah.
All right, everybody gives me
All right.
a warm applause.
Thank you.
Oh, amazing. All right, it's time for some closing remarks, if my computer allows it. All right, it's been lovely to see all of you stick with us the whole day. We have a very important question that we need to revisit as a team. So please scan this QR code and tell us, do you think, after participating in this workshop and seeing the arguments presented by the researchers we saw today, will vision language models make robots safer? We want to hear from you. We're trying to get a statistically significant number of samples from you all to put this question to bed. All right. So hopefully all of you had a chance to take a photo or find this link. I want to say a really, really big thank you to all of our keynote speakers. It was thanks to them and the fact that they came here to talk about a lot of foundations, but a lot of frontiers as well, as we just heard. It is thanks to them that we get insights onto what is coming next in robots, and specifically in robot safety in the era of foundation models. Our oral talks were all nominees for the Best Paper Award. So just to recap, we had runtime observation interventions make vision language action models more visually robust. We had Let's Talk About Language, investigating linguistic diversity in embodied AI datasets. We had adapting diffusion policies to human preferences via reward-guided fine-tuning, and robot utility models, general policies for zero-shot deployment and new environments. It's my great pleasure to say that the outstanding paper award for our workshop goes to Let's Talk About Language. Will the authors please come up? All right, so just come on up. We'll hand you the award. We'd love to take a photo with you. This is really fantastic. I think Rohan's going to take a photo for us. Thomas will hand you the award. You guys should stand together. It's going to be so cute. Congratulations. I can stand too. Yay! Fantastic. All right, it's time to talk about that poll. So now it's time to reveal where we were before. Now we're quickly collecting your data, okay? We're doing some number crunching in the background. But just to see where we were when we started this entire workshop at 9 a.m., pre-workshop, I was actually very surprised. Pre-workshop, I mean, we had 29 responses, okay? So we can get up to those hundreds next time for the second inaugural, the second workshop on safely leveraging VLMs, ICRA 2026. But we, out of the 29 responses, about 72% of folks said, yeah, VLMs are gonna make robots safer. Am I ready to reveal? I gotta refresh. Okay, let's refresh. Let's see the answer. All right. And internet willing, it increased. 86% of folks now think vision language models will make robots safer. We actually got more responses. This is great. We also asked you all any thoughts or takeaways you'd like to you'll keep in mind in your research going forward. Leveraging priors, don't replace classical methods, augment them. Lots of caveats. We learned about lots of caveats, how these models are used, what they're used for, how they're evaluated. We need a lot more interpretability research to understand what's going on. We got to make Hadas happy. And along the road of making Hadas happy, we got to make more informative evaluation. All right, so it was our great pleasure to run this workshop for all of you. Thank you for coming. I want to say a big shout out to my co-organizers. Thomas is down there. He was running a lot of the show. Please stand up. Let's give him a round of applause. And then we got Rohan over there. Please stand up. Let's give a round of applause. All right, and then let's do one more round of applause for all of you. Let's go. All right, so thank you for coming. It's goodbye for now. Please come tell us your feedback if you want to if you want to be engaged with running this in the future, if you want us to run this again in the future, if you hated this and you want us to never do it again, please come tell us. Otherwise, I'll see you guys at the rest of the conference. Take care. Yeah, I'll stop.